So welcome everyone. Like I said, it's a big honor to welcome this workshop. I'll join here so because of the mic. It's a big honor to welcome everyone to this workshop. The workshop is really important to us because it focuses on certain aspects that we find impactful for society, which is process control and efficiency and sustainability. So that's some of the topics that we take into account when we look into projects and we look into partnerships. And so quite naturally, rheology is a fundamental aspect of what we do daily here at PIEP. So we're very glad to have this workshop partnership with Anton Paar, so and MT Brandão. So they're long-standing partners, MT Brandão in particular. And so it was a joy to be able to find common ground for this topic. So I'll be very brief. I have a small video that introduces PIEP to you guys, and then I'll have just a few words on what we do daily, no more than 2 minutes, and I think I'll give the word to the experts, which is why we all are here today. So hopefully the video...
The world is changing. Global population is projected to reach 9.8 billion in 2050. We will be more, live longer, and need more goods. To meet population needs, the use of plastics will increase because of their useful properties. In sectors like automotive, aeronautics, space and defense, construction, packaging, energy, healthcare, and medical devices. We must take action, foster innovation, and enhance plastics to support our society's climate and digital transition. At PIEP, we transform ideas into realities and lead the drive for change and innovation through inclusive collaboration with companies, universities, and research centers. We believe that together we can achieve more. Our work covers different topics of specialization, including climate transition, sustainable and advanced materials, eco-design for innovative solutions, advanced manufacturing processes, composite solutions, digital transition and transformation, quality assurance, and education and training. Our primary focus is on creating innovative solutions that will shape the future. We are your innovation partner, committed to fostering intelligent, sustainable, and inclusive growth. With this commitment, we aim to create a future that is not just innovative, but also sustainable and inclusive for all. PIEP, Innovation for Society. Little choppy video, but here it's doing fine. It's the feed rate apparently, so I have to improve that one. So the small conversation that I want to have is on the importance of this topic on PIEP here. We've been working hardly on two great topics. One for sustainability, of course, and we have a team dedicated to that. They do a lot of LCA, but you can only apply these techniques on good processes, and that's what we want to do. Now, we have a team that's here right now. They're basically compounding extrusion and advanced materials, and we do a lot of work with compounding. And as you might imagine, characterization, sensorization, and digitalization of these processes is essential to what we do. And I'm pretty sure that for our companies, it is as well, because Europe has a need for efficiency right now. Right now, I think one of the topics, and we discussed this yesterday with Florian, actually, there was a big rage on bio-based materials, which are very important to the sustainability of the sector, I would imagine. There's still very ongoing discussions on microplastics, etc. But nonetheless, I think that's certainly something to explore. But as you might imagine, Europe right now is exploring the advanced materials. We're talking about high-end polymers and configurations. We're talking about PEEK, we're talking about PPS, we're talking about PEI, we're talking about a number of materials and applications for space defense, for instance. And certainly you cannot do this without having some autonomy on the subject. And autonomy also implies that our companies are capable of ensuring quality, of ensuring delivery times. So these are right now, I would say that, well, this is a trend, I would imagine, but I think it's a trend that will stay, looking at the geopolitics of the planet. I would say that's a trend that will stay. And so our companies and our institutions should look into these topics even more, because we'll certainly be asked to delve into it by our companies, and we're talking about European companies as a whole. So that's why this topic, I believe, it's not only important for us as Europe, but for the rest of the world, because you have a place in the ecosystem, I would say, in terms of Europe, that is a sustainable perspective on what we do. And so I think we should strive for getting better on these topics, certainly. So thank you everyone for joining the workshop. I'll give the word to Loic, and hopefully we can exchange in the coffee break some perspectives and insights. I think that's really important. That's why we are all here as well, for collaborations, and we're certainly open to those. So thank you. Loic, please.
Okay. Bom dia a todos. I will talk in English because we have people here from everywhere. But this is about Sociedade Portuguesa de Reologia. Eu estou aqui em nome da Sociedade Portuguesa de Reologia, with the invitation of MT Brandão for this session. When MT Brandão has the idea to organize this workshop, they talked to us, and we accepted to show up and to brand it as, yes, this is a real rheology interesting topic. So this is why I'm here. And I take the opportunity, 5 minutes, to talk to you about this society, what it is, and why you should join. So, a Sociedade Portuguesa de Reologia is a Portuguese society. It's about 40 people right now. I'm saying 40 people because these are the people who are paying the fees. But the community is a little bit larger. You have people from the companies, you have people from the academia, from the companies, MT Brandão, PIEP, or Socius. And basically what you get if you join the society, where you have access to experts to help you with any rheological question. And you have access to the European Society of Rheology, and you have access to the International Society of Rheology. So basically you have access to a world of more than 5,000 specialists in rheology, from pharma, food, plastics, bitumen, asphalt, and all these kind of things, because as you may understand, rheology covers many areas of materials. So, how to join? Well, you go to the website, which is spr-rheology.com, or you just Google Portuguese Society of Rheology. Then you go there, how to join, and you will find your way to the forms and to the things to do. Because this is not showing up, and it's not a big problem. How much? For academia, for regular people, below 25 euros per year. For students, these are 15 euros per year. For companies, these are 100 euros per year. And for this, you have access to some prizes. So each year we have the prize for the national prize for the best PhD thesis. You can have access to grants to travel in some events, or if you want to have some education in rheology. You have access to information about all the rheology labs in Portugal and also outside of Portugal. And then you have access for free to all the possible webinars or events that the society organizes. Each 2 years there is the Iberian meeting of rheology. Each 4 years this Iberian meeting is located in Portugal. So if you join the meeting, if you attend the meeting in Portugal, you have automatically 2 years fees for the Portuguese Society of Reology. I will be the whole morning here if you want to learn a bit more about the society in Portuguese. I will be happy to answer your question so that you will know more what you gain by being part of the team. Okay, that's all. Enjoy the workshop, which I believe will be very good. Thank you.
Good morning, everyone. I don't know how you feel about the picture. The thing is, when I look at polymers, I still get kind of excited. And it's really, really nice to see that there are so many people who share the same enthusiasm as me. Interestingly, like when people don't really think about polymers, these are materials which typically work in the background. So if you just think about your day, you brushed your teeth, you got in the car, or like in public transportation, you arrived here, so you already came in contact like hundreds of times already with polymers. But the normal human being does not really think about it. They only think about polymers if something goes wrong, if it breaks, if there is some, if there is anything like we do not wish. But the thing is with polymers, like it's not their fault that they break or that they do not behave as expected. Like the main cause is the processing. And so polymers remember how they're being treated, and this is how you get like certain mechanical properties for the end application. So today we're gonna dig a little bit deeper on material characterization techniques and also on polymer processing techniques. I brought a couple of experts with me. Maybe I start introducing myself first. So my name is Florian. I'm the Global Market Development Manager for Polymers and Rubbers. I work for the company for over 3.5 years already. I used to be a product manager for inline viscometry first, then I was with our FTIR spectrometer, which we're also going to show later on, and now I'm in the current role. I brought a lot of experts with me, some in physical form, some like online. So the Rio presentation will be held online by our Rio polymer rheology expert. Then I have Jiri with me. He used to be the global product manager of our DSC, which is our newest or latest product line. And then we also have our product specialist for extrusion and mixing on polymers. So all of the people I brought with me are gonna give the theoretical presentations, and later on, as Luca already said, we're also gonna do some hands-on parts. So first we're gonna learn a little bit about the basics, and then we're actually gonna try the instruments out together. I can also go here. So Anton Paar, I don't know how many people in here are familiar with Anton Paar. I mean, mostly people know us for our rheometers, for like polymer, for getting like viscoelastic flow behavior, for example, or also dynamic mechanical analysis. But the interesting thing is there is so much more to that. So in total, we have over 16 different product lines, and all of these product lines are tied to different technologies. So I already named a few, like thermal analysis, FTIR, we also have processing now. And why is there even me, or what am I doing in the company? So I'm coordinating all of the product lines internally and also externally. So my goal is to get market feedback, share this with the product lines so they actually work together and provide better solutions for the market. you're probably wondering why Anton Paar suddenly has got such a, he's doing so many, I don't know if you've seen it, but we do a lot of polymer events lately. So why is that? So in 2023, Anton Paar acquired Brabender, which is a German company, like a manufacturer of polymer and food and feed processing units. We also have an example over there, which is like a single screw extruder, but there's also so much more to that, but I will come to this later on. So there's a funny coincidence combining these two companies. Why is that? So Anton Paar has got over 100 years of experience in analytical instrumentation. And the funny thing is that Brabant, on the other hand, has got over 100 years of polymer processing know-how. So what we are currently doing is we're combining the 100 years of lab and our material characterization with 100 years of polymer processing know-how. And we also brought like one specific example with us for today. What's the framework of the seminar for today? In general, as I said, we have 16 different product lines. So we also have process sensors and stuff. So we typically could also start here somewhere at the beginning, where we extract crude oil, which we then break down into naphtha, and then you know the steps. But we are going to talk about the polymer processing today. So raw materials, formulations, how to characterize them, how to fine-tune them. Also a little bit part is going to be recycling. So we're just going to stay here. Like, do not be afraid. It's not about just polyolefins, because I brought a polyolefin example. I'm a petroleum engineer, by the way, so that's why I brought this example. But also these characterization methods also work for bio-based polymers as an example. So polymer processing. So Anton Paar created an ebook last year. It was actually 1 year ago, where all of the product lines got the same kind of samples and polymer samples and formulations and additives and fillers, and they characterized them. So we did a combined work in which we created an ebook, which is also like in here, I don't know, in your bag, there should be like a piece of paper like this, which shows like an industry circle and some additional information here. And down here we have a QR code. So if you're interested in anything, because we cannot dig super deep today, this would like blow the framework. So if you're really interested in getting like a specific application, like really dig deep, then you can use the QR code. It's a free ebook. So then you can also like get a little bit more insights on a later stage. So how is the ebook structured? So we start with the raw materials. Could be any polymers, could be copolymers, any additives. So we want to make sure that we verify the quality of the raw materials. Why is this important? Because if my raw materials are trash at the beginning, then also my end product will not have like good quality, obviously. So now we verified all of the raw materials, and now we know everything is perfect. So what's the next step? Now I go into the formulation. So I'm testing on a very small scale, like new formulations. I mix like the polymers with additives, like some fillers, like stabilizers, whatever you actually need. And then you will actually use a mixer to do this on a small scale, for example, and then you verify it. And what you can see here, that the technologies are always like kind of tied to the segments, so that you get an idea of which technologies you can use in which step. When we're happy with the final with the formulation, then we want to scale it. We want to understand how does it behave on a bigger scale. So in this case, we go into a twin screw extruder. So we do the actual mixing on a bigger scale, so we actually understand how the formulation behaves there. If I'm happy with that, then I have my formulations. I will go into a single screw extruder and just press it into a form or in a shape, and or I even pelletize it afterwards, and then I can share my information depending on which. Like, I mean, there we have so many different participants, so this depends on even you have a like final product, or you share like a master batch, for example, or a formulation with your end customer. Then also a final product production and how to verify that. There are also a couple of techniques how to do this. And then last but not least, we also have a little bit of recycling there as well. As I said, we have a lot of different product lines, over 16. And the thing is, how do you structure that? So I would say most of my time I'm sitting at the airport, traveling from one place to the other, and I collect market feedback or data. So I came up with this industry circle idea just to show, and this is also here on a piece of paper on the handout, that we can talk a little bit more about what actually Anton Paar offers. So there's much more than that. I also have a second circle with me, but this is typically, these are typically, I would say, the must-have. So this is what you typically see at polymer laboratories or polymer entities. So I start at the beginning here. I mean, you're all aware polymers are viscoelastic. So depending on how you shear them or which force you put onto them, which temperature, they either behave more elastic or more viscous. So this is why you would use a rotational or oscillatory rheometer to get an idea of how does my polymer formulation behave on a viscoelastic level. How does it behave at different temperatures? How does it behave at different shear rates? You can get a lot out of information on that. So you can also use a rheometer, for example, for foaming, for polymer foaming, if you want to get an idea of how, when I foam a polymer, how does it behave during that process. Then from the viscoelastic thing, we go to the more elastic part, or like the dynamic mechanical analysis. So instead of a polymer melt, I'm using a solid sample. There are different ways how to do this. What's actually the reason why you do dynamic mechanical analysis? You want to understand how your polymer behaves in real life situations. I always have a very, very simple example for that. So let's say you have your bag, your shopping bag, and you know that the glass transition temperature is somewhere around 50 degrees. Let's just assume that. And then I purchase some ice cream in the store. And then my wife or my girlfriend just tells me, come on, we have to hurry up, we have to pick up the kids or do anything else. Then eventually I start running. And so I have not just a thermal impact, but also a mechanical one. So if I'm below the glass transition, for example, I can probably run. I can run. So even if I run really, really fast and there's a lot of stress on the shopping bag, I will still make the way. Let's take an absolute absurd example, and I have a lasagna with me, which is far above, it's a hot lasagna, so it's far above the glass transition. Then I have the problem already that the bag is gets softer just because of the heat. Maybe it holds, I assume that it will still keep the lasagna in the bag, but if I then have the case and someone calls me, says we have to hurry up, and then I start running, what will eventually happen is that the bag just bursts and the lasagna is on the ground, so I have to purchase another one. So this is a very presentative example of why dynamic mechanical analysis is of importance. Then this is actually or maybe this is also an update. We have both instruments here for the practical part. We have over 50 years of experience with rheology. And on the first week of October last year, we actually launched a new series. So we moved from the XX2 to the XX3, which is a huge step also in accuracy and also features. Then our newest product line would be thermal analysis, the TAN with the Joule DSC. So why do we use a DSC? I want to understand how my polymer behaves on a thermal level. So how is this useful? I can use it either to find glass transition temperatures. I can do melting. I can also see cold crystallization in the material. And additionally, I can use this information to find the process window for processing. But more to this later on. Then we also have FTIR. This is also something pretty new. The instrument was launched in 2023. And this is there for material characterization on a qualitative or quantitative level. Typically, people use it qualitatively, that you just compare two different batches with each other and then get an idea if the formulation is the same or not. I also brought an example where you can also use FTIR to quantify additives, for example, in the polymer formulation. Then I have something unique, but something not as often used, Raman spectroscopy. A quick question, who of you is using a Raman? There. Really? Yeah? Graphene? Okay, this is a prime example. So yeah, I mean, the main struggle with Raman is FTIR is the much more potent solution for polymers, but there are some applications where it actually makes sense to use Raman. So for example, if you're working with hydrogels, which have a lot of water in there, typically the water peaks would overlay the whole FTIR spectrum. So in this case, with Raman, you actually get much better results. Or if you're working with graphene, this also works very, very well. if you remember, I was talking about 100 years Anton Paar, 100 years Brabender, and this is where we actually like found the first connection. So what we are doing is we're combining Raman with different instruments. So first off, like for a couple of years already, we combine, as you can see, a rheometer with Raman, which you can use to get a chemical and physical insight into the during like a rheological measurement. And also, and this is something new, we also combine Raman with extruders. Single screw extruders, twin screw extruders. We're also working on mixers currently. Why is this important? With Raman, you can actually monitor inline crystallization, for example. You can measure composition of the formulation. If you have any stabilizer in there or you do reactive extrusion, you can also understand via Raman what's actually happening inside the extruder. Then down here, we have our Brabender equipment. It's about polymer processing. So first moisture analysis. We also have the instrument here. This is something, I would say, like it's a unique method because we are not using a titration solvent or just a balance. We are working with a method called calcium hydride. So how does it work? Why is it special? It's water selective and it's the most precise way how to measure moisture. So you would have like some sample, you put it into the sample chamber, then the instrument creates a vacuum in the sample chamber, and then we're gonna start heating up the sample. And what's gonna happen is that all of the volatiles and the moisture will go out in, will leave the polymer matrix, but calcium hydride only reacts with water. So hydrogen will build up, and from this pressure increase, you can actually calculate the moisture, and this goes down to an accuracy of 1 ppm. Then processing, we have like different scales of processing. So the smallest we have is like a mixer with 50 milligrams of sample volume where you can test formulations, and then you can also scale up to twin screw or single screw extruders in all different shapes and sizes. So they go from 60 grams per hour up all the way up to 100 kilograms per hour, depending on what you really need. Then the last two are, like I would say, also like something new. Is anyone using gas picnometry currently? Is anyone familiar? Are you guys familiar with gas picnometry? So this is used to measure the density of polymers. Typically, what you do is you have your polymer, then you hot melt, like you melt it, you hot press it, then you have a specimen which you put into water, and then at a specific temperature, and then you wash it out of the water displacement. That you get then you get the bulk density. The problem is this takes a lot of time, typically 40 minutes to an hour, depending on how good the operator is. Gas picnometry is like an alternative way to do this. So there is no sample preparation. So you take your polymer pellets or your final product, you place it into a sample chamber, close it, and then we're using an inert gas to fill the whole sample chamber. And the instrument can calculate from the gas displacement the actual density. What's the advantage besides having no sample preparation is that you also can measure open pore porosity, for example. If you have some PU foams or any polymer which foam, you can also get the foaming density or also the porosity of your sample. This is also important because like if you have a polymer pellet and there are already like there's some air trapped inside, and I do the water displacement, I will only get the bulk density of the sample. With gas picnometry, it will actually tell you how much air is trapped inside, or if there is air trapped inside the sample. And the last example is intrinsic viscosity. How many of you are measuring intrinsic viscosity? Anyone? No? Typically, so I'm going to be quick on this. So typically, intrinsic viscosity is measured with a capillary viscometer. Everyone who runs these tests know they're very sturdy and takes a lot of time. We have like an alternative approach, so it's a rolling ball viscometer. So you also have a capillary, but in the capillary you have a ball which rolls either from the top to the bottom or vice versa. How does the measurement work? You have an inclination, so you can actually adjust the shear rate. And then you just then you dilute the polymer in a solvent. Each polymer has got its own unique solvent to use. There are ASTM standards for that. And then you place the sample into the capillary and you measure the time it takes for the ball to go from the top to the bottom or vice versa. And the longer it takes, the higher the intrinsic viscosity. Why is this important? Because from intrinsic viscosity you can also calculate the K value or the molar mass. if you don't have a GPC, this is a much cheaper and faster version to do this. I don't know how long I have. Oops. I will not go in detail here. This is just to show you how much Anton Paar actually has like additional techniques, which are sometimes a little bit more R&D focused, or which are actually niche applications. So we just to give a general overlook, we have particle characterization here, dynamic light scattering. We also have laser diffraction. So if you're interested, if you're working with paints or you want to check the colloidal stability of your sample, you can use like DLS. We also have surface analysis. So if you treat your polymers and you want to understand how long you have to treat them in order to achieve a certain property, then zeta potential can be used. We also have refractometers and also combined systems. So you can combine, for example, like a RE instrument with the Lovis, for example, a density meter. So in one run you get multiple results. Then down here we get super special. We also have surface and scratch testing. So there are smaller versions of this for non-orientation testing, that you get an idea of how homogeneous the surface is. If you're working with paints or coatings and you want to understand how the coating is like sticks to the substrate, you can do also like a scratch test. So you just non-indent, then you pull the sample and you increase the pressure, and then you get an idea there as well. Then also we have XRD, if you're interested in in crystallization hierarchies, for example. We also have SAX, so small angle X-ray scattering. Then we also have oxidation stability. I would honestly just use a DSC for that, but the rapid ox is just like a simple way how to measure how stable your material really is. Then we also have for sample preparation for ICPOS, for example, microwaves. We also have a microwave synthesis if you're doing some synthesis in your lab. Then last but not least, as I said, we also have inline sensors with density, refractive index. I mean, there's a lot to that. We also have flow meters now, but this is more, I think this is not really relevant here. This is more for the production scale. And then last but not least, our rheometers, all of them, I forgot to say that, they are modular. So you can use one rheometer, use it for powder characterization, use it for DMA analysis, or you can also use it for just simple rheological assessment. So this is it from my side. I wish you like a very interesting day and a lot of fun. Please don't be shy. If you have any questions, just like ask those questions, because this makes it a little bit more interactive. Yeah, so I will hand over now to our colleague. He's sitting in Graz. He will give a real presentation.
Hello and welcome. So my name is Matthias Warduch. I'm a polymer engineer, and I want to try to show you something about the benefits of rheology in combination when you're working with polymers. I will go to basics of polymers. I will give you an introduction into rheology. I will talk about rotational rheology of polymers first, give you some practical examples. Then we will move on to oscillatory polymer rheology, and I will give you a short insight into rheology or extensional rheology, as well as DMA or dynamic mechanical analysis, if we still have enough time. So first question, polymers. It's a very versatile material, so I want just to give you a short overview what we are talking about. Basically, standard polymers are uncross-linked polymers, so like thermoplastics, so we divide them into semicrystalline and amorphous polymers. On the other hand, we have cross-linked ones, so we have thermosets and elastomers. And there's a third category which doesn't fit in one or the other because it's something in between. So, for example, thermoplastic elastomers and vitrimers. Today, I will basically focus on thermoplastics, and we will have a short look also into thermosets and elastomers. But in principle, we can characterize all of them with our rheometer. So let's start with basically the standard polymer. So everything that we consider as a polymer is usually a thermoplastic. And here we start with the uncross-linked thermoplastics, so we can divide them into amorphous thermoplastics and semi-crystalline thermoplastics. They have a very wide range of mechanical properties, so they're very versatile. So we can use them for many, many different applications, no matter in principle what we want to do with them. So that's is making them very powerful materials. And the nice thing about them is that they can be melted and reprocessed. So once we have it in one part, we can regranulate them after usage and just reuse the material newly. They can be used, for example, like in extrusion, in injection molding, thermoforming, and all the other standard material processing processes. And then we have the cross-linked polymers. They are a little bit differently because they cannot be reprocessed. So once they are cross-linked, so they are permanent cross-linked, they stay in their shape. This makes them a little bit harder to recycle or to reuse. But on the other hand, they have some really nice and cool features, which makes them very, very helpful in many applications. So they are very heat resistant, they are rigid and strong. But as I mentioned, they cannot be remelted. So we need different kind of processing mechanisms. So like compression molding, reaction injection molding, raising casting, and so on. And there is a second second material class that is a cross-linked polymer, which completely behaves differently, but in the end, the idea behind is the same. So they are also permanent cross-links, but the main difference here is that the permanent cross-links is much, much less dense. So the material cannot be remelted, but the material is still flexible. So we don't have that many strong bondings between the chains so that the material can have the properties that we want them to have for the application as a rubber product. Again, there are different ways to manufacture them. In principle, we talk about different curing methods. So for example, you can use chemical reactions, or you can also use irradiations and others. So this depends a little on the system, how you build your elastomers. And the way you process them, basically there is also compression molding, injection molding, but this works a little bit different than for uncross-linked polymers. However, the processes are also usually using heat and time to get the materials in shape. And they, again, cannot be reprocessed that easy like thermoplastics. Here we have a short overview of the materials, of the different materials. So we start on the left-hand side with the two materials that are thermoplastics. So the amorphous ones show a thermogram. So what is a thermogram? It's basically the mechanical behavior of a temperature. So here we see the material stiffness in red. And when we cross certain temperatures, the material is getting softer and softer. So here the green line, this is the room temperature. And amorphous thermoplastics are very, very rigid and strong in this area. And also here, but here we have a temperature where it starts then to flow. So we cannot use the material in this area anymore. When we have a semi-crystalline polymer, the things change a little. So here you can see the glass transition for amorphous is far above room temperature, and for thermoplastics, it's below room temperature. So this means we usually use this kind of materials when they're already in a somehow flexible state. So this means we already have this first transition behind us. For elastomers, it's again a little bit different. So we have here room temperature in green. We have the glass transition far below room temperature. So this means in this area, so for example, at minus 100 degrees or something like this, the material would be very, very stiff and very rigid. And once we are over this glass transition, the material gets much, much softer. And here we have the area where we use this kind of materials and where we can benefit of the specific material propositions that are due to this low, sparsely cross-linked system. And for thermosets, again, we see that this jump at TG, so the softening, is much less, and this is far above room temperature. So this means we usually use the material in the stiffest way where we have it. Now let's come from the polymers to rheology, so the main topic that we have in this talk. So why is rheology of polymers important? Basically, we want an optimized process. So this saves energy, this saves material, and this gives us a better a better product quality in the end of the day. So every polymer process, in principle, depends on the flow behavior of the material, and this is what we characterize using rheology. So we can get an optimized process and more efficient and higher quality. Of course, we want to develop materials as well. For this, we need to know the molecular structure which can be analyzed, but also we want to know what happens if we, for example, combine different kinds of polymers, if we add additives and so on. So, and this all influences the material behavior and the flow behavior, and this can also be characterized very well in rheology. Then a point which is, I think, the most important for all, quality control. It is an easy tool just to get information if my material is always having the same quality. So if I have, for example, a new material, a new batch, and the product quality goes down, most likely there is something wrong with the material. Of course, you can do MFI measurements, which I will explain a little later. But in the end of the day, if you want to get a full picture of the material, you need to do rheology. And to be honest, it's not much more complicated and not more time intense than doing a simple MFR measurement. And the fourth one is not really rheology anymore. It is already going into the direction of DMA, but this can also be done using our rheometer. This is performance prediction. So I want to know the mechanical properties, the thermal properties of my material in the conditions where I want to use them. So this is also important to get a good quality and a good result in my product in the end of the day. I already mentioned the MFR or MFI melt flow ratio. This is a very common used way to characterize materials because it's very easy. So what we do is we have a polymer, we put it into a barrel, heat it up, melt it, and use a weight just to press it through a defined nozzle. And in the end of the day, everything is defined for the different kind of polymers. So we have a certain temperature. In this case, it's, for example, 190 degrees, and we have a certain weight. And then we wait for 10 minutes and see how much material is pressed through my nozzle. We have pros and cons of this. It's very, very easy to perform, and it's very, very easy to interpret because we get a single number and we see, okay, this has a low MFI or it has a high MFI. But this pro, that's only a single number, I would say is also a con because we don't get any more information. So we don't have a clue how my material behaves at a different temperature. I cannot compare different materials because I'm not able to correlate the MFI to my process directly. Because if I have different MFI values, I get different shear rates. So for example, if I have an MFI of 1, the shear rate applied in the nozzle is about 2 reciprocal seconds. Whereas when I'm having an MFI of 5, for example, it's approximately 10 reciprocal seconds. So we are looking at a different spot on the viscosity curve. And we have no clue how my material behaves at the real conditions in my process. So this is a huge drawback. So now let's have a look into rheology itself, so how it works and what we do characterize. In principle, we can see here, we can characterize everything from very, very liquid to very, very solid. The question is always which kind of measuring system we are using and which kind of movement do we use. So for example, down here we have rotation. So rotational tests can be used for everything that is somehow liquid and flows. And the more solid the material is getting, that harder it is to do rotating tests. So therefore, we would basically use oscillatory tests. And oscillatory tests have the benefit that they can be used for every kind of material, from very low viscous to very high viscous, so even to solids. Here we have our nice new device, the MCR 703 in this case, so it's the XX3 series. and we can use it, as I mentioned, for oscillatory and rotational tests. First, let's have a short look at rotation. So basically, we measure shear rheology. And the value that we get out is just viscosity or shear viscosity. On the other hand, if we do oscillatory tests, it is also shear rheology, but we get out much, much more. So we get the complex viscosity, we get the complex modulus, the storage and loss modulus, and the loss factor. It is the same kind of measurement. It lasts comparable long, but you get much, much more out of it. And what's the differences and what's the benefits, I will show you a little later during this presentation. And additionally, in rotation, we also have the chance to have a look into the extensional rheology of a material, which will be covered in the very end of the presentation. So we get extensional viscosity and strain hardening index. So I already teased that the geometries have a huge importance. So because, of course, if my material is very, very low liquid, so it has a very low viscosity, we need a different measuring system than we are measuring a solid. So we're starting from very left with the concentric cylinders. So here you have basically very, very liquid-like samples, like polymer solutions. If we're going to higher viscosities like melt, we have plate or cone plate systems where we can characterize polymer melts in rotation and in oscillation. And you see here that they are on the same level. So in principle, they can be used for the same kind of materials. The difference is that the cone plate system has the advantage that we only have one shear rate over the whole diameter of the measuring system because of this cone, which is not the case here, but here we are calculating the correct shear viscosity, so we get basically the same results. And the drawback of the cone plate system is that you have a very small and defined gap, and this is probably sometimes a problem if you have a filled material. So here the particle size is important. For extensional rheology, we have this kind of fixture. It's called the SER tool, sand-mounted extensional rheology tool, which is basically used for films and fibers. And then we have our solid-like materials. So we have different kind of solid fixtures, which will be covered in the DMA part. And we also have some powder cells that can be of benefit to use, which I will not cover within this presentation here, but we can also do powder rheology, just as a side note. What is measured during a rheological test? In principle, it is quite easy because we just apply a force and we measure the reaction of the material. We know everything else. So we have a defined square area, we have a defined gap or height, and we know the force because we measure it and we apply a certain speed. And based on this, we can calculate our shear stress, our shear rate, and our viscosity is basically the combination of shear stress and shear rate. And based on this, we can characterize our material, how it behaves under different conditions. Why is this important? So in principle, we can differentiate between three kinds of materials. So ideal viscous materials, so this is number one. So this means the material stays constant over the shear rate, so the viscosity. So this is, for example, something like an olive oil or something like this. There is not really an dependence on the shear rate. Then we have two. These are the shear thinning materials. This is what our polymers look like. So this means the higher the shear rate, the lower the viscosity. And there are also shear thickening materials. This is, for example, starch measurement, also starch samples with high content of starch. So if you apply here a higher shear rate, you see that the viscosity goes up. But today we are going to talk about the second thing. So like polymers are shear thinning materials. Why is that? Because of the inner structure of a polymer. Polymers have chains and side chains, and they interact with each other. So every molecule is beginning in rest, so they interact with each other, and then the viscosity is high. And if I apply a shear rate, I start to move this polymers, and the inner chains start to deform and then to start to slide on each other. And then the resistance goes down, and we have disentanglements, and the viscosity is also getting lower and lower. So if we want to compare this with a measurement, we see here a standard viscosity curve with a shear plateau in the beginning at low shear rates, and we increase at a shear rate, and we see at a certain point the viscosity starts to decrease. So what's happening here? In the beginning here at the blue spot, we're entangled like we have seen on the slide before. Then we start to move and move and move and do some orientation. And when we are at the red spot, the material looks like this here. So we have shear orientation. And now if we just let the material go again, so we just take the force away, the material tries to get back. So like entropy, it's going over time, it's going back to its relaxed state. So this is what's basically happening during viscosity measurement. Now the question is, what can I get out? What can I see out of my viscosity curve? So in principle, we can compare materials with different molecular weight distributions or molecular weights. If we have different molecular weights, we see here three materials, they are basically the same, but the molecular weight is just shifted from PS1, so it's polystyrene 1, with a high molecular weight to PS3 with a low molecular weight. And as we can see, the shape of the curves changes, especially in the beginning, where we see with a decrease of the molecular weight, also the zero shear viscosity decreases. If we go to higher shear rates, the material itself behaves basically the same, so it's not that high impact. But at low shear rates, the impact can be very, very high. And if we have a material with a different distribution, so they have the same average molecular mass, but a different distribution, we see the plateau is the same, the high shear rates are basically the same, but here in the middle, something changes. So if we have a more narrow distribution, this area is a little bit at a higher level than a lower one. So we can directly see, if we compare same materials, the impact of different distributions and different molecular masses. We can also get information about the filler content of materials. So here we can see a standard curve of an unfilled material, and now we increase the filler content. And as we can see, with an increased filler content, we also increase the zero shear plateau. And if we have a very, very high filler content, it might be that it is just increasing without any plateau in the end, so which is not measurable anymore. And this is just because we have interaction between the molecules, which are then breaking up over when I apply a higher shear rate. So far to the oscillatory tests, to the shear viscosity test. Now let's come to the oscillatory tests. In principle, they are doing the same, but we don't apply one rotation, but we have very, very small movements. So it's like moving left and right, with a defined amplitude and a defined frequency. So like we see here, so this is what we apply, a stress or a strain, and this is what we get back. So we measure stress or strain, and we measure the other one, so the one that is not applied. And what we can see here, that there is a certain phase shift. This phase shift is correlated to the viscoelastic properties of a material. If we would have a completely solid material, a completely elastic material, there would not be a phase shift. If we have something water-like, there would be a phase shift of around 90 degrees. Now, let's have a look at the different kind of tests that we can perform. As I mentioned, we do oscillatory tests, and this gives us the option to change a lot of things. So we can do amplitude sweeps, so where we just, like in the upper picture, increase the amplitude from one point to the other. This is basically done to get information about the linear viscoelastic range. Then the most common test, I would say, is the frequency sweep. Here we get the complex viscosity curve, the zero shear viscosity, the molecular weight distribution, and so on. And for other applications, for example, if we want to do DMA, we do temperature ramps, or if we want to do curing, for example, we can do time ramps. So just a look what happens during an amplitude sweep. Again, we have one test point to the other, so we just increase the amplitude from left to right, and we can see here two things. In principle, we see that G prime, which is the storage modulus, so this is the elastic behavior of the material, stays constant over a certain time, and then it starts to decrease. So this means at this point something happens, and this is that we break up the inner structure, so the material is not able to relax anymore and to get back in the original state. So everything that we want to do should be done within this area, because after this point, so if we apply a too high strain, the material will be destroyed and we don't get correct data anymore after this. And the second thing what we see is G prime is higher than G double prime. And this means that G prime has more impact on the material behavior. So this means G prime is reflecting the elastic behavior. So the material is behaving more like a solid than like a liquid. If we have a look at the lower curves, it's vice versa. We have G double prime higher, G prime lower, and therefore the material is more liquid-like. So this would be would be easy flowing. This would be more or less like a gel or like a solid. Now let's come to the frequency sweeps. So once I know my linear viscoelastic range, which I just found out here, I can do a frequency sweep within the linear viscoelastic range. So this means I apply different frequencies, different speeds, and see how the material reacts. This is comparable to the shear rate, as we will see later on. And with this, we just see the material behavior over time at different speeds, and we get information about the material behavior during processing. Why is this important? I want you to give a nice example. This also points out the importance of rheology compared with the MFR. So we see here two curves. The red one is a PMMA or plexiglass, and the second one, the black one, is polycarbonate. As you can see here, we measured this with an amplitude of 1 and with a temperature of 240 degrees C. And we see a completely different material behavior. So in the low frequency area, we see that the viscosity of PMMA is much, much higher, and the viscosity of PC is much, much lower. But if we increase the frequency, then we see, or the shear rate would be the same, we see that the material, so the PMMA, gets to flow much, much earlier. And at a certain point, we have this crossover. So here the material, the PMMA, has a lower viscosity than the PC. This is important if we want to have a look at the process itself, and if we want to combine this material so we can blend PC and PMMA. What happens then? As you can see in green, we have 70% of PMMA, so the material in the beginning behaves much, much more like PMMA than PC. And if we increase the PC content, we get closer to the need PC. However, if we increase the frequency, we see there is an important point. So here, the material, luckily or unluckily, behaves the same. So this means I could not guess from knowing this material behavior, that there is a crossover point where every material behaves the same way. Now, what would be if I would do the characterization using MFI? So in principle, this would be possible, but a little bit tricky since we have different standards for different materials and different temperatures. So this is, if we want to follow the standards, we are not able to do this at 240 degrees and get the right values out. However, if we have this happening, we see that the MFR for these materials is 5 to 15 grams per 10 minutes, which correlates to a shear rate of 10 to 30, which is exactly this point. So from the MFR value, we would get 4 times the same value for PC, 70% PC, 50% PC. only only the PMMA, the neat PMMA, will show a different higher, lower MFI value. So this means this is something where we don't have any information about this behavior and this behavior over there, which is in principle important for my process because the material will behave completely different in process conditions. I told you about frequency sweeps and about shear rheology, and I also already said that you can compare shear viscosity and complex viscosity. This is because of the Cox-Merz rule or relationship, which allows for uncross-linked polymers to basically say shear viscosity equals complex viscosity. So we can translate one measurement to the other. Is this really true? We can have a look. So in red, we see shear viscosity, and in blue, we see the oscillatory viscosity, and we can see some differences. Why is that? Because for the very low shear rates, it is beneficial to perform shear tests over oscillatory tests because oscillatory tests would take very, very long if you want to do them at the very, very low frequencies. And here you get data which within a reasonable time, which is not possible with oscillatory tests. But on the other hand, we see that the curve of the shear viscosity goes down, so the viscosity goes down much, much earlier than in the complex viscosity in oscillation. And this is due to the fact that when we do shear rheological test on an elastic material, the sample just leaves the gap between the upper and the lower measuring system. So therefore, we lose material, and therefore the torque that we measure goes down, and therefore the viscosity looks to go down, which is not the case. So in this case, the blue data would give you the correct results. And additionally, we get the information about G prime and G double prime. Now, what can we do with our data that we just measured? We see here Karo-Yasuda is one of the regression models, and we can use this to get out information about the shear viscosity, which is correlating to molecular weight, which we already seen at the shear tests. We get information about the slope here, which is correlated to the flow behavior of the material, and we get this A value, which is correlated to the distribution of the mass, what I already showed to you as well. And we get this nice crossover point here, which is lambda, which is the relaxation time. The relaxation time is important because based on the relaxation time, you can see or calculate if a process works or not, because there is something called like the Deborah number, which sets a relationship between relaxation time and processing time. And you have to try to keep this as low as possible to be in a good process window. Why is that, or what happens? So we can see here some effects that come from a too high Deborah number. So we have shark skin, we have melt fracture, and we have all these kind of effects in shark skin. And this would not be acceptable as a product in the end because the material surface doesn't look like it should be. And now the question is how to prevent this. We could increase the temperature, we could slow down the process, we could add additives, we could change the polymer. And to know what is to do and what's the reason, rheology is the right tool to find out what makes the process better, because usually you don't want to go down with the speed because speed is time and time is money. Okay, now let's go to some additional information that they get out of oscillatory tests. In this case, the crossover point, so which you only get because you know G prime and G double prime. And this is very unique for every material, and it's dependent on also on the temperature and the combination. And what does this crossover point tell us? It tells us basically again, something about the inner structure of the polymer. So we get an information if we have a higher or lower average molecular mass distribution, or if we have a wider or broader mass distribution. Be careful if you're comparing completely different materials. This approach is not really relevant, but if you compare similar materials, this is very nice. For example, if you do some tests on a material that is reused, so recycled, then you will see an effect that probably brings you to a lower average molecular mass and a broader distribution. There are some other tests that we can perform, which are quite nice and easy. So there's, for example, the TTS. A TTS is nothing else than frequency sweeps at different temperatures and the same material. This can be done with a simple, easy test. So this is not really something complicated. You just start one measurement, and at the end of the day, you get out all the information you want to have and you need. In this case, we did some tests on a polymer at between 160 and 260 degrees. And when you see here what the TTS principle does, it's just shifting curves to a reference curve. So we start with a high temperature, we shift it to the right, and the lower ones will shift to the left. So as you can see, the x-axis is the angular frequency, and so therefore the data fits together. So there's this correlation between the temperature behavior, temperature-related behavior, and the time-related behavior of polymers. And now the question is, does this also work for materials in reality, not only in a simulation? Of course it does. This example is also something that you can find in Rio Compass. Here we did exactly the same test between 160 degrees and 260 degrees. It is, I think, a polycarbonate sample, and we just did several frequency sweeps and we shifted them. In this case, you see the storage modulus over a frequency range that starts at 0.01 approximately and goes up to 10 to the power of 5. So we have a lot of decades of material behavior that can be simulated for a certain reference temperature that you want to have. But as you can see here, it doesn't only work for 3', it also works for 3" and also for the complex viscosity if you want to know this as well. Then something else, the degree of cure. So in this case, we do a test with a disposable sample, a disposable measuring system. We have something like a resin that we put on our rheometer. We heat up to a certain temperature. In this case, it is 90 degrees. And we want to know how long it takes that our material cures. So we just keep everything constant and have a look what happens over time. And we see here in the beginning, 3' is something here below, 3" is here. This means the material is behaving like a liquid. And the longer we keep the material at the temperature, then the material starts to change. And here we see 3' is going up and up and up, and here we have a crossover point. This crossover point is important because this is the trail point. From this point on to the right side, we see that the material is getting more and more solid. And here, in the end, we get a plateau, and here the material is 90% cured, I would say. And if we have different material formulations and different temperatures, of course, the shape of the curves will change. So far, through the 3 rheological measurements. Now I want just to give you a short excursion, short explanation into extension rheology, because this can be also of interest for some applications of polymers. For example, if you do some sheet extrusion, some blow molding, some foaming, here the extensional viscosity of a material is of importance. So far, what we did with shear rheology is what I just explained in the beginning of the talk. This is not relevant for extension rheology. Here we have the sample, and here we do not shear the sample anymore, but we stretch it. So the sample is not getting sheared, but it's getting longer and longer. So we have a certain strain rate instead of a shear rate. And we have a strain instead of a deformation. For this kind of measurements, we offer 3 different measuring systems. So there's the standard one, the SER tool, which is the standard for many, many different other rheometer brands as well. And it is just 2 drums where you apply a sample, you close an oven, you melt the sample, and then you just turn here in one direction. And these 2 drums are connected via a gearbox, and the sample is just stretched in both directions, and you get basically the force that is needed to tear the sample apart. And this can then be used to calculate the extensional viscosity. For a universal extensional fixture, this is something that was designed by Anton Paar. We only have 1 drum that rotates. So here this drum rotates, here the sample is just fixed, and here we stretch the sample and get the same data. The benefit of this system is that we can also do oscillatory measurements because we don't have any gearboxes, and therefore we can do some basic DMA as well using this. And then we have the UXF twin drive, which is basically the same like the SER tool. Here we need a second rotational drive, and we also rotate both drums and stretch the sample, and we get basically the same data like with the SER tool. What is measured, it is a little bit different than standard rheology, as you can see the curves. So we see the extensional viscosity over time, and each curve is just one single sample. So we apply one extensional strain rate for example 1 reciprocal second, 0.5 and 0.1, and we just can see here that the material, depending on the speed, behaves differently. And in this case, we see that the material goes up, so the viscosity at a certain point starts to increase, and this is so-called strain hardening behavior. This is something that you're looking for when you do this kind of processes like foaming, like fiber spinning, because this shows that the material is able to stretch and don't collide afterwards once it's stretched. This, for example, is the case for LDPE. If you go for HDPE, so high-density polyethylene, you don't have the long side chains that can interact. And in this case, we would have a curve that looks like this here and just goes down because in this case, the material is not getting stiffer anymore, and it just rips off. And again, here, not only the theoretical curves, but also the measured curves. We see here between 0.1 and 20 reciprocal seconds for an LDPE that shows nice strain hardening behavior. Here we see this curve. This is the so-called Croton's related curve. Croton's ratio basically tells that you can combine shear viscosity and extensional viscosity with a empirical number of 3, so a factor of 3. And here we see as long no strain hardening is occurring, the viscosity is basically the same. And based on this here, we can then calculate the amount of strain hardening that's occurring, and that's the so-called strain hardening index. If you want to have a closer or better explanation and closer insight, of course, I will be able to give you some more detailed information afterwards, or I can send you some information if this is of importance for you. Now I just wanted to show you a little bit more about DMA. So I think we have about 5 to 10 minutes left. Here we see our MCR 703, which can basically be used as a standard rheometer with just the upper drive, where we can do everything what just was explained before. Then we have a twin drive combination, so where we have this upper drive and the second rotational drive down here, which allows some special measurements where you need to have a very, very high accuracy, or you need some equipment where you need to have 2 movements. And then the third one is the dynamic mechanical analyzer, which on the one hand has the standard rheology up here and the second drive here, but this one is not rotating or oscillating. This is just moving upwards and downwards. And just to give you an impression how this works, Yeah. This is just shear and torsion. Here we have compression, so we just extend and compress the sample. or we can do this in oscillation as well. But these are basically the movements that we want to perform. And like for liquid-like samples, it is also important to have the correct measuring system for the solid-like samples. For example, if we have a very stiff material, we have 3-point bending because we just have a sample that is placed here. We apply normal stress here, and we do some movements upwards and downwards, and then we can apply a certain temperature, and we see transition temperatures of the material. Of course, if the material would be too soft, then it would not be possible to bend. In this case, if we have a soft material, we could use a cantilever system where we clamp a sample here, here, and here, and then the sample is stable, and we can just move upwards and downwards and measure the material behavior over temperature. The disadvantage is that the free sample length is very short, so we have a lot of clamping effects in the measurement. So this means transition temperatures are correct, but the moduli that we measure will be too high. Then we have a solid rectangular fixture where we just clamp a sample below and above, and then we just tear it apart and move upwards and downwards. Here, these are our standard plate-plate geometries that can be used for rheology and also for compression. And the same is for the SRF, can also be used for rotation and oscillation with the upper drive. The principle behind it is the same like in rheology, so I don't want to go into detail. The only difference is that in case of DMA, G double prime or E double prime will always be higher than E prime. It will always be lower than E prime because we have a solid-like material behavior. I just want to give you an insight in material behavior on the example of the PC PMMA mixtures. We can see here again, the black curve is PC, and we can see that PMMA starts to get softer at around 100 degrees, 110 degrees. And the more PMMA we add, we see that we shift all this softening to a right side, so to higher temperatures. And what else we can see is that we have one peak here and a second peak here. This means that the materials still are not one material. So they, even if we mix them and we solidify them, at the end of the day, there are still regions that are PC and regions that are PMMA. So this means that they are not miscible. Just another example for DMA, how it can help us. For example, if we have a fiber reinforced material, we can see, of course, the thermal properties don't change if we change the direction of the cutting of our sample. So this means we have higher enforcement in one direction than in the other, which just leads to a change of the modulus. But the glass transition temperatures and so on, of course, is not touched by that. But we can see the mechanical properties change significantly. And one last thing that I want to mention is a nice feature of our device. So as I mentioned, we can do rotational measurements with the upper drive, and we can do extensional measurement with the lower drives on one sample. So we don't need to change the sample. So we clamp it, we do a torsional test at one temperature, we do an extensional test afterwards, we increase the temperature, we do this the same as again and again. And what we can get then is a nice thing, the Poisson's ratio, because G prime or G star and E star are correlated or are connected with each other via the Poisson's ratio. And since you don't need to change the sample, you don't need to touch it anymore, you can directly calculate the Poisson's ratio based on your measurements. As you can see here in red, these are the extensional measurements. So E values are always higher, G values are always lower. And if we correlate them via this equation, we can then calculate the Poisson's ratio dependent on frequency or even on temperature. And if we have a look here, for PMMA, there is a lot of data available for Poisson's ratio behavior. We are completely in the range where we should be. So this is just showing that our approach really works. So I think I'm at the end of the time, and I want to thank you for your attention. And if there are questions and we have time, I would be happy to answer them.
Okay, thank you, Matthias. I think we can have the coffee break. We come back in 20 minutes, okay?
Thank you. Bye.
Thank you. Bye-bye.
So welcome back, it's me again. I have like a 1 hour block, so we're gonna do 30 minutes of FTIR, followed by 30 minutes of Raman. And obviously we're gonna start with one of the most interesting technologies, FTIR. It's a quick starter. Who is already using an FTIR in their daily processes? Good. So before we actually get started on applications and stuff, I will just we're gonna dig deeper in what actually is FTIR. So I'm gonna start with one fundamental question, maybe like what is actually infrared light? Does anyone have some ideas, like some example of infrared light, maybe? Or should I explain it first? So what is infrared light? Infrared light is part of the electromagnetic spectrum. So it's not visible light. We can only feel it in the form of heat, but we cannot see it. And this is the light source we actually use for FTIR. So now which brings me to examples. Do you know any examples of IR light in your everyday life? What was that?
Remote control from TV. No?
Yes. Yeah. What's that? Mobile phones? Yeah, not that much. Yeah, also, like think about something big, like what a thing, like typically you see every day. Yeah, yesterday you saw it like very, very well. Today it's a little bit cloudy. The sun, yeah, perfect. So this is I would say the main, like the sun emits infrared light. So I'm keeping up with the time. I just give you other examples. Thermal imaging. So for example, if I want to understand if my house is leaking some heat somewhere, I can use IR light to do that. Another example would be infrared cabins. So I don't know if this is a big thing in Portugal. Typically when I'm more in the colder areas, people are huge fans of infrared light cabins. So you sit there and you can feel the heat, or the heat. So this is also, and then also we have FTIR spectrometers, so IR instruments which use IR in order to get like a chemical insight. So how is a FTIR spectrometer built up? I mean, there are like some like key components there. So first of all, I have a light source. I'm just gonna put like, so I have a light source, and this light source emits infrared light. And then it goes into the interferometer. Just for the sake of time, we'll just call the interferometer like a black box. This does some magic. So it goes through the light interferometer, then it goes through the windows which you typically have in an FTIR spectrometer. These are typically KVR, and then we shine, like we hit the IR light, like we hit the sample with IR light, and the organic samples like actually react to infrared light. And some of this energy will be absorbed, and the residual energy goes to the detector, and then we get the interferogram. Also, for time reasons, I will not go too deep onto this, but then we have this magic equation, like Fourier transformation technique, which actually computes or transforms the interferogram into a spectrum. So now principle, how does it work? I take me as an example. So let's imagine like I am a water molecule. So my body would be oxygen and my hands would be hydrogen. So it's summer, the sun comes up, I'm feeling the heat. So now I'm like, yes, like, you know, like I can actually go out, can go like go to the sea, for example, like enjoy my time. And this is actually what happens with organic samples. Like if they are hit by infrared light, they're gonna start moving. And this movement will be captured by interferogram. And then at the end of the day, we have the spectrum. So each chemical, chemical component in there, or composition, like moves, and each of these peaks corresponds with a functional group in your organic sample. So why is this important? So let's say I lose my hair in the room here, and someone finds it. You can probably say, oh, this, I see the hair, I can check it, and I say, oh, this was Florian. And this is also the same thing with polymers, for example, or any organic matter, each of the materials have a dedicated fingerprint, like a spectrum. So I can just, by looking at the spectrum, I mean, for us, like just looking at it is not enough, but with help of PC power, but just taking a look at the spectrum, I can understand the chemical composition of a sample. So this is typically, if my dancing was not enough, this is a typical water spectrum, so you can see there are all different swinging motions, like you can have a symmetrical stretch, bend. There are unlimited ways, I mean, more or less, how the molecules can actually move. And this is actually what you see in the form of peaks. So by just looking at the spectra, it's very hard to tell which kind of sample it is. Just for a human, if you do not know what the material is based on, just because there is so much variability. But if you, for example, know it's a polymer, then just by looking at the spectra, you can tell it's P, it's PP, or like a mixture of that. So in general, for the polymer industry, there are two main ways how to measure, like with an FTIR. So I'm going to start with the first one, which is transmission. So I have a polymer film, and I'm just going to shoot the R light through the polymer film. And some of this energy will be absorbed by the sample, and the residual energy hits the detector, and then we get the interferogram and then the FTIR spectrum. The only limitation to this is that through transmission, like you absorb a lot of energy. So depending on how thick the polymer film is, or the sample thickness is, like you can either have like a lot of saturation in FTIR spectrum as well. So typically it's best to have very, very thin samples. And then we also have, and this is the most commonly used method, it's attenuated total reflectance, called ATR. We have both of the measurement cells here. So what's the difference? Here we just shine through the sample, and in this case we place the sample onto a crystal. The crystal can be either diamond, germanium, or zinc selenite, depending on the spectral range you really want to achieve or get an idea of, and also of the refractive index. So this works with total reflectance. So one thing to keep in mind is that the refractive index of the material has to be, or of the crystal, must be higher than of the one of the sample, because otherwise I don't have a total reflection, and in this case I don't get any signal from the sample, or not enough signal. So how does it work? The infrared beam hits the interface between the crystal, in this case it's a diamond, let's say it's diamond, and like the sample, and some of this IR light will penetrate the sample. The penetration depth depends on the angle, obviously, and also the intensity of the light source, but in general it's between 1 and 5 microns. So you only measure the surface of the sample. This is also something to keep in mind. If you have very heterogeneous samples, then typically FTIR can be a struggle. So you have to make sure that it's very homogeneous. And this penetration we typically call evanescent wave. But this is just like a scientific way how to like word. And then the residual energy goes to the detector again, and then we get the interferogram. For an interferogram, we typically get like an FTIR spectrum. Talking about FTIR, I said there is like no sample preparation, so I just brought some requirements for me. So let's say you have an ATR crystal, and it's very important to like stick to some rules. So first of all, the crystal structure must be clean. Those instruments are very, very sensitive. So just breathing at the instrument will show you a CO2 peak. So it's very important that you actually clean it very thoroughly, that you actually, that you only measure the sample you actually want to measure, and not something like some external influence. Then also for solid samples, it's very important that the contact angle is, or that the contact is very firm. So you want to make sure that you get a lot of pressure onto the sample, that actually the sample covers the full part of the crystal. Otherwise, you will not get as much intensity. Then also preparation for solids, there is not real much sample preparation. I mean, there are some exceptions, obviously, like everywhere, that if you have very, very, very hard samples, that you maybe have to actually make powder out of it to measure it to get like a better signal. But in general, for polymers, you're very good with just the solids without any sample preparation. And then we also have liquids, so you can also apply any liquid or gel or paste, so semi-solid. So you can technically apply anything. The only thing to keep in mind is do not use this pressure clamp on liquids, because otherwise you will push the liquid off the crystal. And then last but not least, best practice. This is always like a thing of the user. Some people take background spectrums all the time. Some people do them every 2 hours. Why do you use a background spectrum? As I said, these instruments are very, very sensitive. So even moisture or CO2 will be picked up by the instrument. So what you do is you record all of the external influences. The instrument saves this as a background, and then it will subtract the background from the actual sample, so that you only see the sample, not anything else. A rule of thumb also, if you know that there is no CO2 like in your FTIR spectrum, and you can see a little peak around 2400, that's typically CO2, that's the message to say, okay, now the notification, now I need to do a background spectrum. Okay. Oh, that's interesting, now it works. Then I skipped quite a bit. So now application overview. What are FTIR spectrometers typically used for? So first of all, and this is the most common thing that what typically everyone does, is verification. So let's say I produce a specific, I have like raw coming goods in, like a verification. So I have a raw material and I want to check if my supplier actually, I bought the right formulation from my supplier. Then I can just take the sample, put it onto the FTIR instrument, and then verify if the received sample is actually, or material is actually what I'm expected to receive. What you can also do is, let's say you produce your own polymer formulations, and then you want to get an idea if the formulation is actually, has got the right composition, is actually the same what you, like a gold standard, for example, so you have your reference, then you would compare the freshly produced batch with your reference or with your gold standard to actually get like a quantitative idea or a verification. Then what you can also do is that you use this as an identifier when you think back about my hair. So let's say I have a random sample. I also have some samples there at the practical part. So all of the polymers are white I have there. So how do I actually know if it's PE, PP, or PET? I don't know. I cannot tell by just looking at it. So in this case, I can use an FTIR spectrometer. So I can use either my own library on the instrument, or I can use like a purchased one. And then the instrument will let me know from the spectra which kind of material it actually is. And then last but not least, and this is something a lot of people are not really aware of, you can also quantify things. So for example, you can quantify filler content in your polymer formulation. A general rule of thumb is that the detection limit is 1%. Of FTR, but as always, there are some exceptions. So there are also some things which really like absorb a lot of IR light. There you can also go down into the ppm range. There are two ways how to do this, either with a chemometric model or with a linear regression model. So but I will come to this later on as well. So you can use it either qualitatively or quantitatively. And also there are all things like in between. So you can also check for contaminants, or get an idea, like set thresholds, for example, so you get like a much closer idea on a chemical level of what your material is actually about. FTIR applications, I brought some with me. You can see like polymer processing, this is analog, and if you take a close look, you can actually, like FTIR is almost there in every step. I mean, you could also put it into compounding to check the formulation, but as you can see, it's very versatile. You can literally use it in like more or less any state of the process. Just a little bit of delay again. So there we go. So we start with raw materials. As I said, a simple verification. So I receive raw materials, can be polymers, can be additives, could be fillers, whatsoever. And I want to know if the quality of the supply is actually what I expect from it. So I can do like a simple verification test without any sample preparation with an ATR crystal, for example, and get a very, very fast response. So within 30 seconds, I know if the sample I received is actually a sample I would expect. So in this case, you would use a HQI calculation. It's a heat quality index. So what does it do? You have a spectrum, and the software compares the reference spectrum with the actually newly acquired one. This works with the algorithm, which checks on almost unlimited points along the spectrum, and then checks the vectors on it. So just from looking at individual points and their vectors, you actually get a hit or miss. At the end of the analysis, you would also get a report. As I said, you can also set thresholds here. So we said I brought two spectra with me. The black one is the reference, which is the gold standard, and then I have a sample, which is the blue, spectrum. And as you can see, these match very, very well with each other. So I'm doing incoming goods inspection. So I said I want to have at least 95%. Like a hit, like it should be 95% the same sample, and the instrument now checked, and we got a fit of almost 99%. So we are within spec, so it's the same sample more or less. I sometimes get the question, is the baseline a problem for the instrument? So if you have different baselines, this can happen if you have different instruments and stuff. This is actually not a problem because, as I said, the software uses data points and their vector and not like absolute points. So even if the baseline would be very up there and you would see like a huge difference there, it actually takes the vector. So no need to worry for that. There's no no spectral processing needed.
So,
yes, please.
It makes the comparison right away when we make the sample. Because some brands don't have that feature.
Yes, it does. So it depends on what you want to do. Some people prefer to record the spectra, then they do the analysis on their own, but you can also fully automate it, and the instrument will record the spectra and do the verification for you. Okay. You can also fully automate it, for example, then the instrument would do the polymer process, like would do the spectral processing for you and then do the analysis as well. So you can actually, like if you have one person in your lab who is very familiar with FTIR, this person can set up the instrument, and for the operator, they just bring the sample, press measure, and the instrument does everything fully automatically.
Oh, that's good. Because I have one where I made a database of all our products and the standards, and make this comparison. It says a pass or not, but the new one doesn't do it.
Oh, okay. This comes with the software.
You have to make a method to compare this new material.
Mm-hmm.
That's not it.
Yeah, now in this case you would choose all of the libraries. You have typically people have one or two libraries, which are then like with multiple materials, and then the instrument does it fully automatically, and you just get it also. It
just reminds me the near infrared.
Mm-hmm.
You have to put all the data in, and after is much more easy to operate.
Yeah, I mean with NIR, this NIR always works with chemometric models, so you have to have put some mathematical model in there. This is not needed here because you just compare the spectra, so there is no additional work needed. You just like have your library.
But chemometric is needed for the quantification, you said before.
It can be that. And currently we only support linear regression models, but this will be something for the future, obviously. Mm-hmm.
The quantitative is usually not very used, or I want to explore more about the quantitative method.
Yes, I will come to this. I think this is actually the next point, if I'm not completely mistaken. Recipe development. Yeah, there we have the quantification. Oh. Good point. Thank you for the for the transition. So you can also quantify. And we also we just talked about this. The only limitation is that you would need a linear correlation between the filler or the additive or the part, the contamination, and the actual spectrum itself. So how did we do that? I'm just going to give you an example. It's a little bit delayed here. So for example, here we have a spectrum of PE with different concentrations of calcium carbonate. As you can see here, typically you would not have these peaks here, so and it's not very user-friendly to look at it. So what we did, we isolated this specific peak. So what are we looking for? We're looking for a peak or that changes with the concentration.
Responds linear to the concentration.
Yes. So in this case here, if you take a look here, this is 0% calcium carbonate. So there's no peak at all. And then if I have 100% calcium carbonate, the peak is very, very high. And if I have different concentrations like 10, 40, or 20, 40, and 60, you can see that the peak is rising. So there are two possibilities. Either it's rising, so it gets higher, or it gets broader. So then we take a look typically at the integral area, or it can also do both. So ideally, you find a peak which has got this like phenomena behaves like this, and what you do with the software now is that you tell the software, please find the highest peak within this spectral range. So from like this is 900 and 800, for example, and then the instrument will fully automatically mark the peaks, and then you will get a linear regression model like this. So next time when you do like when you measure a sample, what will happen? The instrument will actually measure the peak height in this specific area, and from the peak height, from the absorbance, we can actually calculate the concentration.
Could be also the area of the peak. Could several other peak.
Yes, can also be the area. So you can either choose the peak height or the integral area. So you take the area below the peak. Yes, please.
Yeah, from my own stupid question, what would be typical is the minimum of the detection limits for smallest percentage?
It depends on which sample you have. Typically, it's 1%. This is a spectroscopy. Rule of thumb is 1%. There are also some samples or some additives that absorb a little bit better. Then you can also go into the 100, 200 ppm range. But in general, for calcium carbonate, for example, it's 1%. I mean, the idea here is that you do the qualitative analysis, and then you get an idea of the quantitative as well. I mean, this is not a tool where you say, okay, this is super precise, like 0.5%, for example. This is also very strongly based on how good your base information is. But it gives you like a very good estimate. It gives you, I would say, like the deviation could be like 1 or 2%. So it gives you an idea of how like how much concentration is actually in there. Any additional questions to that? Okay, good. Then extrusion, what we also did, you can like on the final product, so for example, we were comparing peak. So for example, if you have a final product and you want to actually verify the quality of it, this is the same example as with the incoming goods inspection, just on a final product. So even if you have a lot of peaks and you have a lot of information, the instrument fully automatically does the pass-fail analysis for you. By the way, because a lot of people are taking photos, we will share their presentations afterwards as well, so then you get them in a better quality. So you can see here we set a threshold of 95%, and then actually like it passed. Then also, like you can also use FTIR to determine crystallinity. This does not work with all polymers though, so this is a very specific example of peak. There is also an ASTM standard which explains how to actually determine the level of crystallinity. So how did we do that? We were using the ASTM F2778. So we were recording a peak spectrum. You cannot really tell much by just looking at it, so we're just going to zoom in a little bit. And what we are typically interested in is in these two peaks. So we're interested in the peak height. So we record the peak height of both peaks, and then we use those as a ratio. And from the ratio of HA, this is the peak height of peak A and the peak height of peak B, we can actually determine the level of crystallinity. This is based on Sachs information though. So this is the general equation is based on Sachs. So you can also use this. It's just an example to show you how versatile like FTIR really is. Then we were also talking about ATR and transmission cell, and probably the question come up, when do I use transmission measurement, when do I use ATR measurement? So in general, if you have anything liquid or solid and there is no peak saturation, so that the sample absorbs like normally as expected, and you have a little bit lower sensitivity, then you can go with ATR measurement. I would say 95 all applications are using ATR. But then you also have the transmission measurement. So in this case, like you either press a film or you have KBR pellets. So for the people a little bit like more experienced, like 20, 30 years ago, you were using KBR pellets for samples which absorb like not enough. So what you did is you were having like a KBR powder, and then you took a little bit of the sample, and then you like mixed it, and then you get a KBR pellet like this, and then you measured in transmission. This was before ATR time. The problem is everyone, and I did this once, like which prepared a KBR pellet, this is a horrible task. like half of the time it breaks, and then you have to do it all over again, and also you have to make sure that it's very homogeneous. So typically, if you want to have like a very fast and easy measurement, you go with ATR measurement. Then here I brought an example. So if I compare two samples with each other, the same sample with each other on different measurements. So you can see the different sensitivities. So here at the bottom, the blue FTIR spectra corresponds with an ATR measurement, and the yellow one with the transmission. And you can see if I want to verify or identify something with ATR, I have a much easier time, because I get like very smooth peaks, I get like enough information to do like a qualitative analysis. But let's say I want to quantify something, then the transmission comes in here. So you can see here, I cannot get any information out of this because all of these peaks are in saturation. It absorbs like too much. But down here, I can see like a tiny little peak, and this tiny little peak would not be visible on an ATR measurement. So if you're, for example, using, like we had this question with the sensitivity, if you want to see trace amounts like of an additive, like here the PFAS peak, I can spot this only with transmission, because here I get like a lot more response from the sample. Which brings me to my last example. So now we are done with all of this, so we start with the recycling. So how can you use FTIR for recycling purposes? So what we did is we had 3 different samples, one pure virgin LDPE and then recycled LDPE. How did we recycle the LDPE? We just threw it into the extruder like 5 times, and we did some mechanical recycling. And then we also produced mixtures, so 50% virgin, 50% recycled. So how do the spectra look? So the yellow line corresponds with 100% recycled LDPE, the blue line corresponds with only virgin LDPE, and then we have a mixture, as I said, 50-50. And there are some things which point out. So, for example, here we have a peak, which we do not see on the virgin LDPE. So this is also, when we think about the quantification example, this is typically a calcium carbonate filler peak. So this was somewhere in the extruder, probably, which was put into the formulation like during recycling. This is a common effect you see in recycling, which you see some calcium carbonate. And then also we have a CO stretching vibration. We are not quite sure, it's very hard to tell where this comes from, but we think that this is some ester bond which was created during the mechanical processing. And then last but not least, we also have another peak, which is the carbonyl group. So why is the carbonyl group of importance? Like hydrocarbons all have the carbonyl group, which tends to oxidize. So by an increase on this peak, you can tell how old, or you can actually tell if it's a recycled polymer or not. This is typically used in the oil and gas industry, for example, when you look at lubricants. So if you think about the lubricants in your car, how do I know when the lubricant is already used up? Typically you do a viscosity measurement, but the problem with the viscosity measurement is that it's already too late in there, because the viscosity is already thick, because I have some contaminants already in there, which are actually destroying my motor. But what I can do is that I just take a look at the carbonyl group, which gives me the oxidation. And from this oxidation here, I can tell how old actually the sample is. So you can also use this for polymers. Which brings me to the end of the FTIR presentation. Are there any questions? No?
For example, in the analysis of liquids, in my former FTIR, we have a kind of a black lid to put, I think, the liquid don't get out, and I think it doesn't get in the light. Mm-hmm. But for example, these new ones don't have it. Why?
I mean, you have like it's a stainless steel plate with a crystal on it. So if you place like just a drop of it, it will not go anywhere. I mean, it's just on the stainless steel plate. If you want to measure the transmission, obviously you would need this is called a transmission cell, where you fill the transmission cell with the liquid.
Yes, you have that where you have the ATR, you can take it off and have other instrument to make the transmission.
Yeah, so typically what you have is, I have the instrument here. So the instrument, there is a base part of the instrument. So all of the critical components like interferometer, light source, beam split, and everything is in here. And then you have a modular cell in front. So
you can take it off.
Yes.
And for the other.
Yeah, I mean, you would substitute the whole front part of it. So you can open up the lever, take the whole cell module out, place the other one in there, and then you're good to go. This is also like pretty automized. The instrument just knows when the cell module goes into the base unit, the instrument automatically detects which cell is in place also.
Okay. I always work with ATR. I didn't make the kappa BR passives or liquids. It is difficult to make these films or to make the transmission.
You mean the KVR pellets?
Yeah.
I mean, they're also like, this is kind of automized right now. You have pellet presses where you can do that. But I would say for almost all applications, you're pretty good with the normal ATR measurements.
Okay. But the transmission, how do you make the transmission with liquids?
With liquids, so you have a sample cell holder. And what you do is you have a transmission cell, so it looks like it's a these are two windows of different materials, and then you just put it inside, yeah. And the transmission cell keeps the thickness of the sample also constant and holds it in place, and then you just like shoot the IR light through it.
Okay.
You're welcome. Yes, please.
So at the end, you were talking about the Brandão group and how old is the sample, but I can't understand the relation between that peak and how old is the material.
Okay, so if you take the carbonyl group is prone to oxidation. So if this peak increases, then just from increase you know that there is some oxidation going on. This is just like a, how do you say, like a rule, or like, which you can observe with any hydrocarbon. So for example, if you take cable glands, and we had this one customer, this is a nuclear plant, and they're using cable glands. And it's very important that the cable glands are intact, otherwise you will have a problem there. So what they did is they just took a part of the cable gland, put it on there, and just from looking at the peak, they know, I mean, if you have like a fresh cable gland and an old one, and you see a peak there, then you know that some oxidation happened. This can also be used for bitumen samples, for example, where you actually want to understand how old is my bitumen. Typically, all of these industry look at this specific peak.
And how is that connected with the recycle part?
Because if you recycle something, or if the polymer, for example, suffered from oxidation, then you would also see this here. So just by mechanically recycling the polymer, you actually see a difference here. I mean, there is also the chance that this peak does not stem from the oxidation, but also from some ester. So for example, if you have an ester bond here, then it can be also linked here.
For me, it's more difficult because I work with natural resins from pine resins, and like ester pine resins modified, and I already have that peak very large. Mm-hmm. So I couldn't see that small peak because it will be like behind. So for example, when the resins are oxidized, we measure the peroxide value to measure how old they are.
Yes. Yeah, like for some samples you would need an alternative as well. This is the same example with water. If you have a very prominent or very strong peak somewhere, which would overlap with certain characteristics, then you are limited to this, obviously.
Yeah. Mine will be overlap for sure.
Mm-hmm. Yeah, then maybe there's a different peak. So as a rule of thumb, if you don't really know how your samples behave, just take a very fresh sample and then take a very, very old one, compare these two, and then look for peaks which have changed. This is the number. So if I do not know which samples I actually I'm confronted with, this is the first thing I do. I just take different times or something like some change, and I'm observing what actually changed in the product and what do I see on the spectrum as well.
There's nothing related with the peroxide value in the FTIR because with wet chemistry is not very good to measure. If we have an alternative, but not with that peak,
that's true.
Should be another one.
That's true. Yeah, maybe it's another one. It's always worth a try.
Okay.
Yes, please.
I have a question. When we recycle polymer, what's happening is that we're reducing the amount of stabilizers and its initially present. Is it possible to detect the traces, at least the initial amount of the oxidants and stabilizer, and after recycling, can we see here some difference in spectra just to verify this depletion?
This strongly depends on the quantity of the stabilizer or the oxidative. So if it's around 1%, you would typically see it. If it's below that, it depends on which additive it actually is. So I cannot say yes or no to that. We would need to check that.
Okay, thank you.
You're welcome. Everyone good? Okay, good. Then I start with Raman. Am I still good in time? Did someone check? Lucas? Luca? More or less? Okay. I'm above or below? Both. I'm good here. So now we switch from FTIR to Raman. So obviously I start with the same thing. Well, how does Raman work? So instead of an infrared light source, we're using a class 3 laser, which is beyond the visible to near infrared light. So I have a lot of more power, and I do not measure the residual energy from the sample, but what I actually measure is the light scattering. So I take the laser, shoot it into an organic sample, and then I measure the energy change. So most of the light will be reflected, but some part of the light will be scattered. And I actually measure the energy difference of the scattering. So I do not have to dance again. You can also see the dancing here. So as I said, you have different swinging or different stretching or twisting, and this actually you can see in the Raman spectrum. One difference to FTIR is that it's a convocal measurement, so you do not have to be in touch with the sample. So this is why it's typically used in the pharma industry, because you can measure through transparent like bags, for example. This is one advantage of Raman. So what are typical applications? I mean, this is very analog to FTIR. You can use it either to identify unknown substances. This is very good, as I said, with backup bottles or containers, because if I come in touch with like drugs, for example, and I don't really know what it is, I can measure through the sample, through the bag, and get an idea of the sample. So this is why Raman typically is used either in pharma or in defense industries, or also like firefighters or police, just to get an idea of what kind of sample it is. So this is the identification. And then also we can do like a verification, so we can check different spectra with each other, as I said, analog to FTIR. And what we can also do is quantify, and this is really, really interesting. Why? Because you have seen the peak spectrum on FTIR. There's a lot of information in it, which is really, really great, because I can also get a lot of information out of there. But let's say you're mixing two different polymers, so you have a copolymer, for example. Then on FTIR, it's very, very hard to actually quantify, let's say, the PC content in PMMA. Why is the reason for that is because the spectra tend to overlap with each other. And then you would need some software in order to separate these peaks and then actually quantify them. So this can be like quite a struggle. So this is where Raman is pretty useful. Because on Raman, on the other hand, you do not have that much information, so you only have a couple of peaks which do not typically overlap with each other. So in this case, you can also use Raman to quantify stuff. But I will come to this later on. And then a huge part is you can monitor chemical reactions, so oxidation, curing processes, for example, polymerization reactions. So you can actually get an idea of how your polymers, or how your materials change over time. Then also molecular structure or phase transition, so you can actually see a change if a sample is more amorphous or more crystalline, and also if you combine it with different technologies, you can also see how the morphology or the molecular structure changes over time. And then last but not least, and this is the thing I will typically focus on now, is in situ real-time chemical monitoring. So composition, homogeneity, melting, crystallization, thermal degradation. I will show a couple of examples there. So where in a polymer value chain does Raman add to the value? So the product manager of this gave me this slide. So it's not analog to the polymer processing, but it's still the same terms. So it's raw materials, recipe development, compounding, extrusion, and recycling. So different use cases for Raman as well. As I said, you can use it either on a qualitatively or quantitatively, and you can also check, do the monitoring across the whole value chain here. Which brings me to the first combination, Rio Raman. We do not have a Rio Raman combination here, but we have the Coral Raman spectrometer with us here as well. So why would I use the combination of Rio Raman? I brought two examples with me. So, and it's already delayed again. Sorry for that. There we go. So I know that that's a lot of information. So just focus on the top here. So we are taking a look only on the physical characterization, on the rheology. So the red line corresponds with the storage modulus. So how elastic is my sample, and the red line here corresponds with the loss modulus. So how viscous is my sample? And what we were observing here was a curing process. So we placed two component material onto the rheometer, and then we were measuring it at a certain heat and a certain shear rate. So we are interested on at which time is the adhesive actually is the epoxy resin completely cured. So if I take a look here, this is the loss factor. So what is the loss factor? The loss factor is gives me the information if a sample is more elastic or more viscous again. So we have this phase angle here. So on a sample which has got 90% phase angle, it's very viscous, and if the phase angle is towards 0, it's very elastic. The reason for this is if I put the sinusoidal force onto a sample, it either reacts right away. So if I push something, it responds to the pushing force right away. So then I have 0% phase angle shift. And if I have something very liquid and something very lazy, for example, and I give it a little bit push, then it will have a little delay. So in this case, it's viscous, so it's 90%. So between 90 and 0% here, we have a viscoelastic range. So this is what we look at. So if I just take a look at the loss factor here, after 1,000 seconds, it's almost 0 degrees phase angle. So the phase angle shift. So I can say, okay, at this point already, the epoxy resin is completely cured. Very good. But if I take a look at the chemical perspective there, so we have an FTIR, we have a Raman spectrum here, and as you can see, there are a lot of peaks. So the first thing to choose is which peak I'm looking for. So I'm ideally looking for a peak that changes a lot during the curing. It either becomes broader or higher or lower. So I'm looking for a massive change in Raman spectrum. And what I did here is I was just looking at one specific peak, and then I was observing how this peak decreases over time. And as you can see here, at 1,000 seconds, it's not fully cured yet on a chemical level. On a physical level, it looks like it behaves very elastic. But on a chemical level, there still needs some time to cure. So when you just take a look at the Raman perspective here, you can tell that it's actually fully cured at 2,000 seconds. So how does the setup actually look like? So you have this Raman fiber probe which you put at the bottom of the instrument, and instead of a stainless steel plate, use a quartz plate. So during the rheological measurement, you can actually get a chemical insight. And especially for more complex curing processes, this can be very, very interesting. Because let's say I have a wind turbine, which should have the mechanical properties, which I typically use curing to do that. Then I want to know if it's actually cured or not. Because otherwise it will eventually break much sooner than anticipated, because the curing was not already fully completed. And then I brought another example. So here we were taking a look at the crystallinity. So we were using HDP and LDP samples. We did the rheological analysis, and then we were looking at how the Raman spectrum changes over time. So let's take a look at the HDP example. So here the red line corresponds with the liquid phase, while the dark line, the black line, corresponds with the solid phase. So you can see there was some melting going on. And again, we're looking for a peak that drastically changes during melting. So we came across this peak here, which is perfect because it's a very distinct peak. But if I go into the melting phase, the peak gets much lower, broader, and moves a little bit to the right. So there's a lot of signal like changing here. So by just looking at this peak, I can actually tell how high the crystallinity actually is, or how amorph a sample is. If you combine this, for example, with a DSC measurement, you can also get an idea of the percent crystallinity during the rheological analysis. So again, you get an idea of the physical part, or the physical information, also on the chemical information. So especially when you think about peak, for example, then it would be interesting, how does my peak behave during extrusion, for example, at the die heads. Then I can do like some, or throughout the whole process, I can actually do the rheological analysis, as Matthias showed during the Rio session, and get an idea of how it chemically behaves as well. I'm gonna skip this. These are just some application reports which give an insight. So we have like on different topics in the polymer space, we have application reports. So as I said, we're gonna share this with you at the later stage. So if you're interested in anything in specific, please reach out, and then we can also share the application reports stuck to these topics. You can see there's always, we already did a lot of characterization. And then this is also something we have here, is the Raman extruder combination. This is something new. We also have the extruder back there and the Raman instrument on top. So why would you actually use Raman during the extrusion process? I brought like a video with me, so I'm gonna try to. Actually working? Oh yeah, here. So this is just like to show you how you would mount the Raman, or connect the Raman with an extruder. So you cannot just like put the fiber probe, put the Raman probe into the extruder due to like the pressure and the temperature influences. So we're using a fiber probe, which it's an immersive probe which you can put directly into the extruder or at different positions on the extruder, along the extruder. Here we were extruding, I think it was LDP, or we just extruded different kinds of polymer recipes, and we were measuring the Raman signal directly in the die head.
It's like an in situ measurement.
Yes, it's an in situ, in real-time measurement, yes. Yes, please.
This is reflection.
This is not reflection. This is light scattering.
Okay, so yeah, so this is the scattering from the laser you send.
Yes.
So the same probe sends the laser and receives the scattering?
Yes. So it measures the energy difference.
Which is back scattering.
What's that?
Back scattering.
It's not back scattering, no. It does not, it change, like, it's only like it measures the scattering itself. Back scattering, like reflection, would not be measured.
Well, so sorry, I don't see the arrangement for that. I'm gonna ask you.
Yeah, we can, yeah. The only limitation on Raman in an extruder is if it's very fluorescent, then you would need a different wave number, like a wave range. Otherwise, you will not get enough intensity. Or if the samples are super black. So this is the only main. So if you have very very dark samples, for example, you would not get like a response from Raman. So why is this important? So we will have an extruder session later on in the day, but typically I also call it an extruder is a black box. So you just throw some stuff in at the beginning or along the extruder line, and then at the end you get your sample, which you then bring to the lab, and then you characterize it. Very easily said. So when I do the formulation and do the compounding or extrusion, I have no clue what's actually happening inside the extruder. I mean, I know the torque and I know the temperature, but besides that, I have no idea what's actually going on a viscoelastic level or on a chemical level. So this is one way how to deal with this. So typically you have, like, as I said, offline analysis, which is very time consuming. So let's say I run the extruder process, then I get my sample, then I take the sample, bring it to the lab, then I do like some DSC measurement, some FTIR measurement, maybe I do some dynamic mechanical analysis, if it's actually like a film or like any specimen in a form, and then I get an idea of how the sample behaves, and if it actually behaves what I would want it to be, right? But the thing is, this takes a lot of time. So if any of the properties, let's say thermally, it does not behave as intended, I have to go back to the extruder, change something on the recipe, and repeat the whole process. So this takes a lot of time. And also when I scale it up, like on this, or scale up, like a part of the process, this can also be like the sample could behave differently. So this is why, like, in situ Raman analysis is really of use, because there are all different kinds. As I said, you can measure the composition or the homogeneity of a sample of this of your melt, and you can also see how it behaves thermally. Yes.
A different thing for melting is softening point, as we measure in the natural resins. Are you familiar with the softening point?
I'm not familiar. I mean, if something chemically changes on it, you would typically see it on FTIR, on the Raman spectrum.
It's similar like a melting.
Yeah, I mean,
why you use here Raman instead, for example, of FTIR?
The problem with FTIR is that the light source is only its infrared light, so the power of the light source is not as high. So you have a rough time using FTIR on an extruder because just of the light source intensity. So this is why with Raman you have a class 3 laser. So you can also have like a 3 meter long cable. You do not use any intensity of light source. That's why you use Raman.
Let's get out of the extruder. For example, if it's in the big reactor, I was interested in see the characteristics within the big reactor of tunnel. Can we measure with an in situ Raman?
It depends on how high the pressure and also the temperature. So what's the temperature range approximately?
Could be between 100 and 295.
Okay, so this is, I mean, typically the Raman, the immersion probe has got the maximum limit of like 275 degrees. So I think you can push like 300. This would be possible. We would need to test it. But we have not tried this in a reactor yet. I mean, what we also do is that we can also put the Raman probe into our microwaves or into our synthesis microwaves, so we can get an idea of the chemical process. But we have to try that, obviously.
Yeah, and also a difficulty should be how to clean it from batch to batch. For example, here in the extruder, you also have this problem. And when you change the recipe, you have to clean the
I mean, this is not a problem. It's a screw. So you just screw out the immersion probe, and then you just clean it. So cleaning is not like such a big topic when it comes to the immersion probe.
Okay.
It's not like fully immersed. You know, it's just like it's a tiny bit. The main issue is how homogeneous is your sample. So if you have if it's very heterogeneous, like just like at the start of the reaction, then you typically would not see much. But at the later point where it gets homogeneous, then you would actually like get the most information out of it.
But here we are in the small conditions, like a bit that is immersed. But for example, in the big reactor, no samples, things will be scaled up.
Yes. I mean, the thing is, like, this is also like it's a single point, like you have a focus point of 600 nanometer range, like on an area. So this is where you actually get a signal. Mm-hmm. So you cannot just like shine through the whole reactor and then get a feedback. This would not really work. But this is also like I come from the process side. So if you think about any inline measurement, it's typically single point measurements. So actually, because like
have you developed these things of in situ in reactors? Are you developing?
We're currently there. No, we're not. But as I said, like if we have a partner who would be interested, we can try it out. I mean, this is.
Maybe we can talk.
Yes, this would also be interesting for the team, obviously, to get more feedback. I mean, this is something pretty new. We started with this 1.5 years ago, and it says like there is a lot of interest in this application. But obviously, like each process is different. So for each process, you would need to do a feasibility study how it actually works. So typically what we do is like we get like the individual components, then we check the final components to see if there's actually like a difference like on a Raman, and then we would include it into the process if we know that the temperature range and the pressure is not too high for the probe.
Yeah, we already know what happened because we characterize with the FTIR. We see, for example, the carboxylic acids decreasing and getting higher the ester part, for example.
Oh, it's perfect.
It's perfectly we see with the other analysis tools, but if we don't have to take the sample from the air with the person, to go into the lab, analyze several parameters, and you have online measurement at real time, it will be a huge increase in the process time.
Yeah, absolutely. I mean, there are also other ways how to do this. So if, for example, you polymerize something, typically the density goes up. So you could also measure this with a refractive index. The only thing with a refractive index is that you would need a high-pass line in order to actually check this.
Yes, I have the reflective index in GPC. I take the sample and go to GPC.
Oh, okay, sorry. So yeah, online real-time measurement. So now I brought some examples. So here, for example, we had a PC PMMA measurement. So we were adding PC to PMMA. And as you can see here, we were observing the composition. So down here, we had a 30% amount of PC and 70% PMMA. And then over time, we just increased the amount of PC. And what's interesting is that here, it's pretty homogeneous. So that the mixture was working very, very well. But up here on the 70% PC, we were not able to actually get like a clear signal. So this could be to two reasons. Either the extruder was not working the way it was, so that's why the sample was very heterogeneous. But for PC, PMMA, what is also interesting is that on a physical level, these two, on a physical level, they mix very well with each other, but on a chemical level, they don't. So you can also use this to get an idea of how your formulation behaves during compounding. So you could do this either with like copolymers or mixture of different polymers, or you can also use this for additives, for example. I just also brought like an example of installation point. So along the extruder, as I said, you have different installation points. So either you can have it directly in the barrel where the mixing takes place, or where the mixing takes place, or you can also mount it somewhere at the downstream part of the extruder, but I will come to this later on. The PC PMMA, I brought like a DNA example with me just to showcase why this is like of interest. So if you mix PC PMMA, so the dark line corresponds only with PMMA. As you can see here, we only take a look at the storage modulus. So at 115 degrees, something like this, you see a drop here. So the sample has here its glass transition temperature. So now if I take a look at the loss factor here, we have one peak here, which tells me, okay, the glass transition temperature is actually there. And we only have one because there's only a single peak. So now if I mix PC with PMMA, which is the light blue line, like it's happening what we expect, that the glass transition temperature is much higher because of the PC part of the mixture. But if I take a look at the loss factor here, I have two peaks. So I have the peak here from the PMMA, and I have a second peak from the PC. So why is this interesting? Because like if you remember the shopping bag, the grocery bag example, the sample actually has got a glass transition. It's got two glass transition temperatures. So, and this is something you could also see on the Raman before that, because you can see on the signal that the intensity the signal was very noisy. So this is also how you can combine like Raman, that you get an idea in the process how your final product would behave in a later stage. Then also this is the second thing, so we were extruding a film. In this case it was a HDPE film, and we were using the Raman probe at the film hall-off. So we were collecting the films all the way when it was actually like already like cooled down. So why is this of interest? Because like what typically happens is if the draw-off speed is very slow. So if I extrude at a very slow speed, the polymer has got a lot of time to cool down and to crystallize. So here you can see if the crystallization, if the draw-off speed is very low, the crystallinity is high. If the draw-off speed is, if I extrude very fast, then the crystallinity is very low. But in here we have this critical draw-off speed. So even if I change a little bit on the extruder speed, the crystallinity changes quite a bit. So let's say you run an extrusion process and sometimes like the crystallinity is very, very good. Sometimes the crystallinity is not within specs. Then this can be due to that you operate the extruder at this critical draw-off speed. So this is another application how to show that just from during extrusion, you can actually tell the crystallinity of your sample. And then we have the installation point inside the die head, what I was already like teasing a couple of minutes ago. And here we can get like a whole different picture. So now there we go. So here we have like the extruder again, the Raman analyzer, and then the fiber probe just inside the die head. So what's interesting there? So here you can see the Raman spectrum. And again, we are looking for a change in the Raman spectrum. And as you can see here, with different temperatures, I also get like a little shoulder here. So the software, with the software, we're taking a look at this little shoulder over here. And you can see it here. So the blue line, this is like a little bit confusing, but the blue line is the temperature, and the orange line is the crystallinity. And what's typically, what's obvious is that if I have a very high temperature, then the crystallinity will be lower. But if we take a look here, we were decreasing the temperature over time, and at some point here, the crystallinity dropped, even though the temperature went down. So there again, you can see like a critical transition zone. So you can understand of how your polymer melt behaves on a crystalline level during extrusion. I have also a different example with PEEK. So PEEK, for example, at the die head shows a completely different behavior. Why is that? Because PEEK has got a shear-induced crystallization. So if I extrude very, very fast, the crystallinity will go up instead of go down, just because the shear is so much on the PEEK. So if you have new formulations and you don't really understand like why it behaves different on the crystalline level, you can also use Raman to do this inline. So you can also like add some additives or some stabilizers and then see how it behaves on a crystalline level. So just to round this up, I think these are the last slides. I lost complete track of time. Perfect. So you can either use it for quality control, that you get an idea. You can also put it like in a bigger scale extruder to get an idea, or you can just get an idea of chemical root cause analysis. So R&D, that you just understand of how your process behaves over time. And this is it. How much am I over time? Again, 5 minutes? Okay. I'm so sorry for that.
Thank you. Thank you again. So I'm going to make my presentation 5 minutes shorter, and then we're perfectly on time. I hope you're not really worn down too much by the excessive amount of information. And I'm not going to make it any better because there's going to be a lot more information. Today I want to talk about thermal analysis, DSC in particular. As Florian has mentioned, we have launched this instrument in October last year. So this is the newest member of the material characterization family of products at Anton Paar. I was the product manager for the DSC, so I was very close to the development process of the device and the software itself so that it does exactly what we want it to do. And now I've changed my role, so I also travel around the world trying to spread the joy of thermal analysis with customers and with our sales subsidiaries and distribution partners. So I'm going to share the joy also with you. If you're not familiar with thermal analysis, I have some definitions. Basically, we can say that any type of analysis that also monitors temperature can be deemed as thermal analysis. I remember during my studies at the university, when we had any lab classes, the first thing that I was asked to put in my lab diary was the date when I performed the experiment and the temperature in the lab. So basically, whatever I was doing was already thermal analysis. However, I would say that more commonly, And more traditionally, thermal analysis is said to be a branch of material science, material characterization. And it's a group of techniques where the material property is measured as the sample goes through some predefined temperature program. And depending on what we actually do measure, we have 4 main techniques, despite the fact that I have 5 lines there. If we're interested in processes that are connected with exchange of heat, we talk about the DSC. That's what we're going to talk about today. But there are other techniques. If we measure the mass of the sample as it changes through the course of the temperature increase, we talk about thermogravimetric analysis. You can simply imagine that as a balance in a furnace. These 2 techniques can also be combined in one instrument where we get the signal from the heat and mass at the same time. Then we call that most often as a simultaneous thermal analyzer. It's not a technique per se, but it's 2 pieces of information at the same time. And then we have 2 mechanical techniques, thermomechanical analysis that measures the dimensions of the sample, so expansion or shrinking. And we can also measure stiffness by a DMA, dynamic mechanical analysis, which you've already heard today because it's in Anton Paar covered by the MCR 5OX now as well, and 7OX multi-drive. And that instrument can actually also measure in the TMA mode, so coefficient of thermal expansion can also be measured by that instrument. But today is DSC, differential scanning colorimetry. Differential because what we do measure is actually the difference between the sample and a reference. Scanning because we scan against temperature or time. If it's against temperature, we're either heat or cool the sample in a dynamic way, or we can keep the sample isothermally at a given temperature for a certain period of time. And colorimetry comes from the Latin calor, which is also in Spanish, not sure if in Portuguese, which means heat, perfect. So we measure the heat flow either from the sample or into the sample, and then we can distinguish between exothermic and endothermic processes. And on the picture I have a cross-section of a measuring cell. Let's see which is the laser, this one. So the sample is in most cases encapsulated in a sample holder, which we call a crucible. Then we have basically the exactly same type crucible on the reference side. The furnace is either heated or cooled. We also run some gas, which creates the atmosphere in the furnace, depending on whether we're interested in inert atmosphere or oxidative atmosphere. That's based on the application. And we also run the gas around the furnace for the purpose of getting any moisture that is unwanted out and create a stable environment for the whole measurement setup. Now, what the DSC can detect. If we talk about polymers, it's mainly phase transitions like melting and crystallization. Glass transition you've heard about in the rheology and DMA section, so glass transition is also a thing for the DSC. The determination of TG is very established with DSC, but the DSC can also shed some light on chemical reactions like polymerization, curing, vulcanization of rubbers, for example. But if we go to even higher temperatures, we can decompose the sample in the DSC, degrade it, and find some information about that. Not really for polymers, but the DSC is a very good tool for detection of polymorphism. Do you know what polymorphism is? No? Don't work with that? So it's the ability of a crystal structure to be present in two or more different crystal modifications. So chemically it's still the same compound, but the crystal structure might be different, and the DSC can actually detect the temperature at which these changes happen. And last but not least, in the first part of this list, I have a specific heat capacity determination, as DSC is actually a perfect tool to assess the CP. So the first part of the list were the material properties or applications that can be directly measured by the DSC. But then we have another whole list of those that are indirectly determined by those that we actually measure from the first half of the list. So if we have not exactly polymer again, but like a pharmaceutical organic compound, by the determination of melting point, we can assess the purity of such compound. If we do a lot of experiments that involve melting and crystallization and different ratios of components, we can also create phase diagrams. At the higher temperatures, under the influence of oxygen, we can measure oxidative stability. By certain approaches in the measurement, we can see and have some insights in thermal or mechanical or processing history or storage history. And one of the last few, material identification. The DSC can also be used to identify materials, but not exactly in the same way as you've seen with the FTIR. With the DSC, we usually measure, and by looking at which temperature we see the glass transition of a polymer, at which temperature we see the polymer melt, and how strong this melting process is, we, by having this knowledge, can assess what kind of polymer we're actually dealing with. And as you've seen with other techniques as well, we can determine good sample versus bad sample, because if we compare two DSC spectra, we again might find some differences that give us some information on this is how the final product should be or should not be behaving. I have some tips and hints on actually how to get the most of your DSC measurement, how to prepare a sample. It does seem like a simple and easy thing, but a lot of the devil's in the detail, I would say, and the detail is the sample preparation. So nice sharp peaks and finally resolved very often are dependent. So the first thing is you need to ensure a representative sampling. It sounds like a simple advice, but yeah, look at your bulk. Is that homogeneous? Then yeah, you just take a little bit of the sample, run it. If not, make sure that you either homogenize or that you run the sample in a duplicate, triplicates, or even more, 4 or 5 times, and then you can do averaging. You receive 5 different curves, you average them, and you might say, okay, now I have a better chance that the result is representative of the bulk. What's very important to ensure is a good contact of the sample with the crucible bottom, with the sample holder, because this is actually the path of energy from the sample contact with the crucible bottom onto the sensor, where I have the thermocouple that senses the temperature and temperature changes. And if I do not have a good contact, then of course I'm losing information. My peaks are getting broader and shallower, and of course then my resolution goes wrong. So good contact of the sample with the crucible bottom is one of the most crucial things. Then you need to select the right crucible, because we have different types, different materials, different shapes, and the closing mechanism. We can either keep the crucible open or close it. Depends a lot on the application and the sample type. If we have like a polymer pellet, then it's very easy. We can use an open crucible. If we have a contact with the atmosphere very desired, that would be the oxidation experiments. Then I'm not going to put a lid on the crucible, nothing like that, because the oxygen which is in the furnace, I want to be able to diffuse into the sample and create the desired reaction. But if I have a sample which during the heating might be foaming or spitting or expanding a lot, then I'd rather put a lid on to make sure that the sample doesn't really creep out of the crucible and contaminate my sensor, which is something that I want to avoid, because then I would need to clean the furnace. And yeah, I'm not a very big fan of cleaning, whether it's a DSC or my room at home, so not really. Powder samples, yeah, we can also measure powders in the DSC. Then I would always go for a crucible with a lid, because of the manipulation and handling. If it's a very fine powder, like a very fluffy thing, then between the time that you actually take the mass in a balance and you need to move it around to the instrument, you might lose the material. And if your sample mass is not very accurate, then of course the quantification goes bust. Because if I'm telling the system I have 10 milligrams of sample, but on my way I've lost 2, then of course the quantification is no longer valid. In polymers, we might very often have samples in the shape of film or fiber, and these samples are very prone to actually change its shape and dimension as we heat them. They might actually shrink or expand, meaning that I would lose the contact with the crucible bottom. So there we also have some nice things we can compress the sample down into the crucible by putting a lid and compact it down, meaning that the mechanical movement is not going to affect my measurement. And then some more general advices. Do not overfill the crucible. Use like 40-50% maybe of the total crucible volume to allow for the expansion and foaming, and avoid the sample actually creeping out of the crucible. Sometimes it's important to avoid mechanical or thermal stress, because even tiny changes in mechanical preparation of the sample can induce changes in the glass transition, for example. And what should be the typical mass? I would say for polymers, 5 to 10, maybe 15 milligrams is usually good enough. So you don't really need much of a sample. You'll see in the afternoon how the sample actually looks like and how it sits in the crucible. And this is something that we can discuss also at that point. And then we have the sample. We need to develop a method. We need to start the measurement. There's a couple of parameters that we need to think about. The first one is to define the objective. What it is that I want to find out. I've experienced too many times when I was at the university and I've had my thermal analysis lab, and it was also a service lab for other departments and other research groups. And my colleagues were coming to me and like, I have this sample and I'm interested in a DSC measurement. And I was like, that's perfect. I'd love to do that. What do you want to see? What are you interested in? It's like, I want to see the DSC. I was like, here it is. That's the machine. What is the outcome of the measurement? What is the sample going to do? I was like, I want to see the overall DSC. He was like, no, you don't really understand. Do you want to measure the glass transition or the melting or crystallization? Or is the sample going to cure or oxidize? This is very important. Otherwise, it's just like a blank. There are situations like that, of course, where someone gives you like a completely unknown sample, but then you need to take special cautions in like the temperature range is probably going to be wider, sample amount is probably going to be smaller, because what if there's going to be a huge amount of heat coming out of the sample and the sample might burn. So yeah, but in order to get good results, you should know what you want to do. And then you define the temperature range of the measurement based on the objective, of course. So if I measured a sample today that I was provided by the local guys here from PIEP, and they said, this is a polylactic acid. I was like, okay, good. So it should be a glass transition below 100, then it should melt. So I'm good to go to about 200 degrees. And I don't necessarily need to heat the sample up to 600 or 700 degrees, because I know that that would decompose, but that's not my objective. So I reduced the temperature range to something that was making sense to me. I have two time details there. Start 3 minutes and end 2 minutes before and after the last effect. Why do I do that? We need to achieve a certain portion of the DSC signal before the effect actually happens to record a baseline. And very similarly, after the effect. That means I need to see the DSC signal where no effects are happening. That helps me then to create the possibility for integrating peaks and analyzing the results, because I want to see nothing before and nothing after. How to calculate that? That's quite easy. It's 3 times or 2 times the heating rate. So if I'm heating 10 degrees a minute, 3 times the heating rate, 3 times 10, 30, I need to start 30 degrees below the first expected effect. Typical heating or cooling rate that is being used in a DSC. In the past, I was very evasive when someone asked, like, so what's the typical heating rate in a DSC? I was like, that depends on how much sample you have and on the application and on the ranges and if it's a strong effect and weak effect. And there was like an hour discussion on what should be the heating rate. Now I'd say 10 degrees a minute, you're good. It's like a golden rule in DSC. If you don't know, this is something that we usually work with. Of course, you can heat slower if you have close-lying effects and you would like to separate them. Slower heating rate will help this. Or you can even faster. If you have weak transitions, like a weak glass transition, the higher heating rate you use, the stronger the signal becomes. So faster if you have weak transitions, or if you need to suppress kinetic effects. So second-order transitions and chemical reactions, the faster you heat, the reaction will happen at a higher temperature. It's very similar For example, the glass transition, the higher the heating rate, the higher the temperature of the glass transition will be. And this is for DMA and rheology the same. It's a frequency dependent or heating rate dependent feature. So that's something that we need to calculate with and might help us. Atmospheric control, I said that the furnace is actually purged with a gas of interest. In most cases, it's going to be an inert gas like nitrogen or argon. But we're sometimes interested in seeing the oxidation of the polymer or any other material, meaning that we would go for either air or oxygen. But there are some special gases that we can also use, like helium, which is a very high heat conductive gas, and that also helps us with separation of close-lying effects, for example. And my favorite is the last bullet point. Make sure your DSC is calibrated. So it's like with every other instrument, the DSC needs to be calibrated. If it is, you can get good results. Now I have two examples which show how important it is to select a good temperature program from a measurement. Most of the examples that I'm going to show, you've heard at least like bits and pieces of those from the DMA presentation or the FTIR presentation, and you'll see how things actually come together from all the different perspectives of the material characterization. This is an example of a cold crystallization of PET, it's a material that you know very well. It's used in the plastic bottle production. And in this case, the cooling rate affects very much or suppresses the crystallization during the cooling. So in this, we have heated the sample from room temperature up to about 300 degrees, every time 10 degrees a minute. But before, we cooled the sample down from a melt with several different cooling rates from 1 up to 150 degrees a minute. And there's two main effects that you can see. One of them is in the area between 150 and 200 degrees, where with the lower cooling rates, we see no effect happening here. But the higher the cooling rate is, starting from 10 degrees a minute, we see there's an exothermic peak being shown, upward facing peak. That's the cold crystallization. Meaning that when I cool the sample down from the melt up to 5 degrees a minute, the sample has enough time and is enough relaxed so that it can actually crystallize during the cooling. But the higher the cooling rate was, we saw the crystallization peak during heating, so cold crystallization, meaning that the sample didn't have the time and space in order to crystallize during the cooling process. And this is also manufactured in here, which is the glass transition of the PET. With the slow cooling rates before, we have actually prepared a highly crystalline sample, meaning the glass transition is quite weak. The step is not as pronounced as in the case of the sample that was cooled very fast and was created mainly amorphous because the crystallization didn't happen during the cooling. The crystallization then only happened during the heating. And whatever happened before, the sample always melts at the higher temperatures. And another example, I said that there are some special measurement modes or approaches that we can take. One of them is a heat-cool-heat, so a repeated heating. First we heat the sample, then we cool it down with a defined cooling rate, and then we heat it again. Why do we do that? During the first heating, we would see sample properties with all the thermal history or processing history or storage history, where what we do with the history during the first heating and cooling, we either delete it, erase it, or we unite this history, meaning that the second heating gives us the actual material properties with the united history. So this is an example of PET again. During the first heating, we see the glass transition at around 100 degrees. We see there's like a tiny little endotherm here, and then something like broader here, which might be effects related to the relaxation of the sample, because during the manufacturing, we gave the sample some properties. But then if we heated the sample up, cooled it down and heated it again, we see like a textbook example of a glass transition with a tiny little bit of enthalpy relaxation. But it's a much nicer step, which can be analyzed in an easier way, and we don't actually see these effects anymore. So cool heat is a very common thing in a DSC, especially when it comes to looking at thermal history. And now I have a couple of application examples. You will see and hear the sample types and the information that you already heard before from my colleagues, and how the processing can be actually seen by the use of the DSC. The first one is actually a very different one from those that my colleagues have shown. These are battery separators. So yeah, Florian mentioned that as one of the first things we come across polymers in different applications without even knowing it. So sometimes we say this is the battery industry or energy storage industry, but the materials very often are polymers as well. So in this case, we've had 3 battery separators in the first site that look exactly the same. It was a white thin film of a material. And by running the DSC, we have received one with a melting peak at about 130 degrees, the other with the melting peak at about 160 degrees, and the third one with actually 2 melting peaks. By having the knowledge of how polymers melt and how they behave, we can tell that the first one, the blue one, is made out of polyethylene. The red curve actually comes from a material that is a pure polypropylene battery separator. And the last one actually showing us the 2 melting peaks. We see that this is a sandwich material where both the components are included. So the polyethylene melting at the lower temperature enables an early thermal shutdown in case something goes very wrong. But at the same time, the polypropylene gives the battery separator a higher structural integrity, I would say. Thus, we can, by blending or actually creating a multi-phase separator, giving it the final properties that are indeed needed for our application. This is something that you've seen before by Matthias and by Florian as well. This is the polymer blend of PC-PMMA, and this is the perspective that the DSC offers us. So again, we have a glass transition from the raw polycarbonate and the glass transition from the raw PMMA, and then the 3 blends with different ratios, 30-70 through 50-50 up to 70-30. And this is the outcome actually. So what we see, one glass transition, of course, for the individual components, PC, PMMA. In the first site, when we took the samples, the PMMA was a transparent one, the polycarbonate and all the 3 mixtures were white in color, so they looked exactly the same. But we see that all the blends show us 2 steps in the heat flow curve, meaning 2 distinct glass transitions. Furthermore, we see that the glass transition always happens exactly at the same temperature as of the neat and individual component that it's coming from. So there's no shift in that. And that actually can lead us to the conclusion that the PC and PMMA, from the perspective of the physical mixing and blending, is a non-miscible polymer blend. Although we have one nice compact material coming out of the extruder, by running the DSC analysis, we can conclude that this is not a miscible polymer blend. How would that look like if we would have 2 components that create a partially miscible blend? The 2 glass transitions might still be persistent, but they would probably be closer to each other, meaning that from the perspective of changing the specific heat capacity, which is what glass transition is in a DSC, they affect each other. And if we would have a fully miscible polymer blend, those 2 glass transitions would most likely become one. I'm not saying that that would be exactly in between the 2 TGs on the individual components, but there would definitely be a much more affecting of one component to the other, and we would actually see most likely one glass transition step. Another example is cure monitoring. Do you work with resins? I do believe some of you do. We can monitor the curing reaction in a DSC very nicely. As we heat the sample up, we see in this case, it was an epoxy resin where nothing's happening until we reach 100 degrees. Then we have a huge exothermic effects with a lot of energy released, over 500 joules per gram, meaning that the cross-linking has happened, and at a temperature of 150, 160 degrees, we have fully cured the material in a dynamic way. So we heated the sample from room temperature to about 190 degrees, 10 degrees a minute. Good. We see the curing is proceeding, the cross-linking network grows into a fully cured, highly cross-linked structure. That's it. But that's one nice thing, how to look at curing. But what we also did is we took the material and we looked at the recipe that the manufacturer of this resin is telling us. And the recipe said that to achieve a curing which is sufficient, we can also do this isothermally at a much lower temperature. You see here we heat it to about 180, 190 degrees. But the manufacturer says it's enough if you heat to only 150 degrees and stay there for an hour. You can perform an isothermal curing. So we did, and then we compared. So the red curve is the dynamic heating. That's the one where we heat it to 200 degrees. We see a nice glass transition at somewhere below 120 degrees. And the blue curve is the isothermal curing for an hour at 150 degrees. Based on what the manufacturer was saying, we see a glass transition at the same temperature with the same intensity. So we might conclude that was good enough. But we thought, okay, maybe we could try something slightly different. We will try to fool the material. We will only heat to 120 degrees, but we will leave there for longer time, for 2 hours. See if that's fine. And the result you see by the green curve. We then cooled the sample and heated again. And you see at the moment where the glass transitions start, I see another exothermic reaction happening. So the glass transition is not even fully finished, meaning that the curing isothermal at 120 degrees, despite the fact that we took 2 hours, was not enough. And we see a post-curing exothermic reaction, meaning that the curing was not sufficient. So the DSC is also a tool how we can monitor the curing reactions and say if the curing was sufficient enough for the application that we need. Florian has mentioned like a wind turbine blades. So this is something where DSC is also being used as a quality control tool to find if curing was sufficient. I've mentioned that if we take samples to higher temperatures under the influence of oxygen, we can also monitor oxidative stability, which can be done in a very simple way, but there is a list of international standards, either ASTM or ISO standards, that actually tell how this oxidation stability can be measured, monitored, what it means, and how it's supposed to be performed. So in this case, we have an LDPE material. We perform the OOT analysis, oxidative onset temperature. This is a simple experiment. You just take the sample from room temperature under the atmosphere of either air or oxygen. Air is considered an oxidative atmosphere. Although it's only 20% of oxygen, that's good enough for oxidation to happen. And we heated the sample up. At the temperature of about 120 degrees, we actually see the sample melt. And then at temperature of about 265 degrees, we see a strong exothermic effect, meaning that the oxidation in the sample has taken place. It has changed the sample irreversibly. And we might say that the oxidative onset temperature of this sample is 265 degrees. That's very nice. We can also have a look at the other approach, which is called OIT, oxidation induction time, which is performed slightly differently. Because first we heat the sample dynamically to a given temperature of the test, in this case 230 degrees, in an inert atmosphere of nitrogen. So that's the black part of the DAC curve, and we actually see the material melting there as well, so endothermic peak. Then we switch to an isothermal mode for 5 minutes in order to equilibrate the temperature of the sample. That's the gray part. And once we are receiving a horizontal line in there, once equilibrate, we switch the nitrogen to air or oxygen and keep monitoring the heat flow. And after about 26 minutes after we've switched, we see again an exothermic reaction taking place, and that actually denotes the oxidation induction time of this material being 26 minutes. Now that as a value on its own seems interesting, and we might be able to report this. For example, if we manufacture material And the companies that are buying the materials from us are interested in the determination of that. But what is the practical importance? Let's say, for example, this was a polyethylene. Polyethylene is often being used as a cable insulator. And it is important to know what is the oxidative stability of that material. However, in most cases, we need the cable insulators to be colored. We need to have a red or black or brown or blue color. So we put a dye or a pigment during the processing. Then we run the OIT analysis again to see if that dye or pigment has affected the oxidation stability of my polyethylene matrix. And I might receive a value, originally I had 26 minutes, that would be 23 minutes. And I might say, okay, so my oxidative stability has decreased a little bit because the oxidation time is shorter, but that might still be enough. However, putting the pigment into the material, I might have changed its structural properties, or they were not good enough from the very beginning. So I put a filler in, like calcium carbonate, which we have also seen. Then I run my oxidative stability measurement, OIT again, and I receive much lower value, like 18 minutes, and that's not even sufficient for the material to be used. So I put stabilizer into the system, and then I run my OIT analysis again, and then my value increases to 30 minutes. And then I might say, okay, this is good enough oxidative stability, and the final processed product can actually go to the market and I can actually sell it. So the OIT measurement is actually a nice tool to see how various components that I add to my matrix can affect the stability of the sample. Fill the material product. I just said that we can fill a material with various components for improved characteristics. So that's the case of a polyethylene and calcium carbonate. Mixing polyolefins with calcium carbonate can happen for several purposes. First, the filler is much cheaper than the polyolefin. It increases the stiffness and improves the processing or optical or surface effects. So the properties of the final product can actually be fine-tuned by the right content of the filler. And DSC is also a good tool to monitor this content. We've had 4 samples, similarly as before, with 20, 40, 60, and 80% of LDP or calcium carbonate, of course. And we can also assess the content of calcium carbonate or polyethylene, in this case, in the product, because we do it in a slightly different way. Using the FTIR, we were assessing the amount of calcium carbonate, but we see a melting peak of the polyethylene, and by integrating the area of the peak, we know the amount of energy that was consumed during the melting process. And very similarly, if we do that for various concentrations and a linear regression, you can see that the confidence is 99.96%. We actually have a calibration curve. And then if we take an unknown sample, we can easily assess the amount of polyethylene in the filled product. So in this case, we're not assessing the calcium carbonate content, but the polyethylene content. But the result actually, if it's only the 2 components in the system, is exactly the same. And in the last one, the last application that Florian was showing was an extrusion, and with different extrusion speeds. So we also performed an experiment. In this case, this was an extrusion of PEEK, polyether ether ketone. And we wanted to see how much the extrusion speed affects the crystallinity of the final product. So we had 3 different extrusion speeds. The highest one was 5 meters per minute, the mid one was 2 meters per minute, and the third one was less than 1 meter per minute. And then the final product was measured using the DSC again. And we see on the first 2 curves, the blue and red one, 3 effects. First one is the glass transition, quite nice. And then the second, at temperatures above 150 degrees, we see an exothermic peak of the cold crystallization. And then, of course, at even the higher temperatures, we see the materials melting. However, the one sample that was extruded at the lowest extrusion speed only shows me the glass transition, which is not very pronounced, again, very weak, but I see no cold crystallization. So this extrusion speed is slow enough in order to for the peak to crystallize during the cooling process. And we can also use the integration of the cold crystallization and of the melting in order to calculate the initial crystallinity of the material. So you see 12.3, 15.9 with the products that didn't really crystallize fully during the cooling, and more than 28% of crystallinity of the product that was actually drawn slow, 0.8 meters per minute. And that shows us that the drawing speed is an important factor in giving the material the final characteristics of the crystallinity. Very similarly, as we've seen with the PET, the higher the initial crystallinity, the lower the amorphous content, and the less pronounced the glass transition. Because the glass transition is the amorphous part of the polymer that is responsible for the glass transition, and it's the crystalline, in case of a semi-crystalline product, that is responsible for the crystallization and melting processes. Not really sure if I made that 5 minutes faster than I was supposed to, but thanks. I hope you've also enjoyed a little bit of heating and cooling of samples, and I'm looking forward to welcoming you in the afternoon by the DSC. If you have any questions, I think we can bring them there or on the way to lunch and back, but I think it's time to eat something right now. Correct.
Hola, good afternoon. Welcome back. We are now having the last presentation for today on extrusion and mixing in extrusion. Thank you.
Okay. Welcome everyone for the last presentation of the day. Hopefully you're not too tired yet and ready for the practicals afterwards. So my name is Carsten. I'm an application engineer for Anton Paar TalkTech, a fairly recently acquired sub for Anton Paar, and we are basically, with our products, we are expanding the Anton Paar portfolio from not only characterizing and measuring to actually processing polymers. So what we do is mostly selling lab scale extruder, single screw extruder, twin screw extruder, but also smaller measuring mixers as well. Sometimes you might ask the question, why do we even need lab scale extruders? Mainly because when you're in a big production line, it's often way too expensive to keep these very large production extruders on hold to do your process development steps. And also our lab scale and small extruder mixers help you get a better understanding of the process. And with this knowledge, we can later on then upscale from smaller scale extruders to the large scale extruders for production layers. And generally in the processing chain, if you want, you can break it down to 3 major steps, which is mixing, recipe development. Then you have the compounding step, which you usually do in a twin screw extruder. And the last step is, or often last step can be done in a single screw extruder, where it goes into shaping the material to the shape you want it to be. So what can we actually impact during the whole process? So the development process usually starts with a feedstock and formulation procedure. So what do we want to make? What do we need? So we have specific polymer architecture in mind. You need rarely processed polymers are just a single polymer. It's often a blend. There are additives, there are stabilizers. How do they behave when they are mixed together? So what we can actually do to observe these mixing behaviors, we can input the input variables such as the temperature. We can apply shear stress by changing the speed of blades or of the screw. We can naturally change the pressure by adjusting the screw configuration, or also aligned with the speed. We can increase the residence time in a batch mixer or in the extruder by adjusting in the screw configuration, and we also have an input on the fill level on a screw or in a mixer. And with these input parameters, what we want to do is finally an optimization of the whole process and what gets into this process, for example, in the processing chain for polymers could be achieve a certain degree of crystallization of your polymer, optimize the reaction time with the addition of additives, optimizing the fusion behavior through the addition of certain kinds of lubricants, in general stabilize the melt stability. And in the end, with the extruder, what we get out as parameters is mainly torque. We can measure the pressure at certain points within the extruder. We can get information about the flow of the polymer melt within our die. Once we open it, we can observe the quality of what we get out of our die. And of course, we can get spectral signatures, for example, if we use a Raman probe measurement. So in the end, the final idea is the machine is a tool to, also the machines that we offer is a tool to understand the process, the whole polymer processing process. Okay, so at the very beginning, when you're in the development of a new material, the first step often is the recipe formulation. How many additives do you want? How do they behave? And for this, we have, for example, a small batch mixers, measuring mixers of different size, where you mainly just test how does your material respond to shear and to temperature. This is especially one of the major applications. For example, the measuring mixer is when you think about PVC applications, and PVC in itself is a very special polymer as it doesn't really melt. It has this fusion or chillization process where you have different stages of particles which melt but fuse together to form a three-dimensional network of particles. And an example curve of a fusion process you can see right here. This was done in a measuring mixer. And this whole fusion test is a very, let's say, important test if you want to optimize your qualities of the PVC dry blend, and if you want to see how can I process my PVC and what's the processing window. Will it degrade? How long can I keep my PVC inside the extruder before it can degrade? So what happens during the test is after you fill in the PVC, you get a short peak, a feeding peak, then the additives start to melt, which is shown in a very strong drop in the torque level. And then once these particles fuse together and the grain boundaries kind of come together to form these three-dimensional network, the torque then starts to rise again until it reaches a maximum, and the network somewhat stabilizes in the end, and you get a continuous process. And usually you would want to have your the complete fusion process within the extruder. So, okay. Then the software also automatically evaluates your fusion time, which is defined in the standard from the filling peak until the maximum of the torque level. So, especially for PVC, fusion time, like I said, is a very important parameter when it's about determining the optimal process window. But there's also other parameters, like, for example, the porosity and the absorption time when we talk about the plasticizer absorption of a raw PVC. Both are linked together, and the absorption time can be, for example, examined in a planetary mixer and is often used as a quality control and as to check to get an indication about the liquid uptake of your PVC resins. Okay, so once we have developed some sort of recipe, another point would be a single screw extruder. A single screw extruder is a very simple setup, let's say. It's often a metering or a corporate pressive screw, so just one screw with an increasing diameter to compress the polymer melt, and usually just three things happen in the material. Once it gets fed inside, it gets conveyed, it got melted, compressed, and finally it gets pushed through the die and to form it into a specific shape. So in essence, it's just a continuous conveying step with a melting and die feeding in the end. Single screw extruders often used just to investigate the melt stability. We use single screw extruders also for viscosity measurement, which I'll come back later to, and also in the end it's basically just shaping depending on the die that is used. Now, a twin screw extruder, a little bit more complex. Instead of one screw, you use two screws, like the name suggests. Our twin screw extruders are mainly co-rotating ones. We do have also one counter-rotating one, but it's a conical. More to this later. And yeah, in the twin screw extruder, you usually have feeding ports at different positions within the liner. This is one example of a screw configuration. The screw configuration is also a very important part of the whole process development. It's basically the most important part. Just to explain this one a little bit, right here we have simple, the material is fed right here at 0D. It's simply conveyed to the top. Here we have the pitch is decreased, which by decreasing the pitch, you get a higher shear, a better mixing, but also we reduce the flow a little bit. And then we have kneading blocks right here, where the material is mixed under high shear. And behind the kneading blocks, we have what we call backwards conveying elements, which which basically blocks the material inside of the kneading blocks to go out until a certain pressure threshold is reached, which increases the residence time, so the mixing time, and then we get a large pressure drop once the material goes over the backwards conveying elements, and we have here a low pressure again, which allows us to feed another material inside. At the end we have the same, another kneading block with a backwards conveying element. When the pressure is low, we could in theory also put a degassing pot inside if it's needed. Okay, so screw design, like I said, is basically the one of the major optimization processes once you are in the compounding part, quite next to the dosing. Our screws for the twin screw extruders can be configured. These are segmented small pieces that can be put together depending on your application. So some of the parts include conveying units, which simply transport the material along the liner. We do have regular mixing units. You can see the difference in the angle. Then we have these kneading blocks, more or less used for distributive mixing, and these high shear cogwheel-like elements, which are more of a distributive mixing, dispersive mixing. Sorry, mix it up. And these the whole screw configuration is in a compounder determines the whole thermomechanical history of your material. Right here you see it again, the pressure profile of the same configuration which we examined earlier. So pressure rises here before we get into the kneading block. Then we get a maximum right here where the kneading blocks are, and after the backwards conveying elements, the pressure drops significantly below. And then we have here another mixing element, and then finally in the die head. But the pressure rises again once it's pushed outside of the extruder. So, in a sense, the twin screw extruder is a continuous mixing process, and the screw configuration is a major part in the whole process development. So what is not shown in the presentation, but it's also quite interesting, especially our twin screw extruders, they come with an open clamshell design, which means you can open up the liner and look where is your material inside, placed alongside the screw. And this is especially really helpful if you're still in the development phase, because you want to see what happens at what place. And just a side story, we had recently a trial with a customer that does battery electrodes, where you have a small amount of PTFE, it's a binder which comes in small particles, and through high shear mixing you want to stretch these particles to long fibers to hold the active material of the electrode together to create a film. And we had this issue, the process worked fine, we started at some point, but what we got out, we couldn't create a film out of it. So we checked, we could just open the liner and check. We had a very large mixing block right here with 4 or 5 kneading blocks chained together, and saw, hey, half of the kneading blocks, our material broke already. So it wasn't really a film anymore, and we tried it by extracting some materials from the end of the kneading blocks and from the middle of the kneading blocks, and we saw that in the middle material was the way we wanted it to be, and this way we could very much decrease the whole screw configuration process by opening the liner, looking at the material, and then just reducing the amount of kneading blocks we need to get the result we want. So the whole extrusion is not just a production process, but also a development platform. You basically bring together multiple factors with pressure, temperature, the screw speed, measure the load of the motor, and observe the torque level, and you naturally have to control the feeder, which is attached to the extruder. Now we still don't know what really happens during the process. As Florian already said earlier, the extruder is a black box, but we can add some attachment to get more information about what happens with the material, for example with a capillary die, which I'll explain in the next few slides. Yeah. So what the extrusion in essence tells us, we have a specific speed of the screw, which we set. We know the torque level or the motor load. We get information about the pressure. We get information about the temperature of our material inside, and we get information about the feeding of the material. Now, what we do not know is viscosity, for example, a big topic, if we didn't characterize it earlier through, for example, a rheometer. Yes.
Do you have a maximum viscosity for the material to get in the extruder? There is.
You mean for feeding?
Yes.
So we do have a few pumps to feed highly viscous material. Mm-hmm. I'm not familiar with the exact limit, but we are able to feed, for example, highly viscous samples like with a honey-like texture. So,
I didn't understand.
So it's possible to feed highly viscous liquids like with a honey-like viscosity. It is possible, but not with a conventional gravimetric feeder, but you need a specific pump for these.
Okay. But I was talking about a product that is solid at room temperature, mm-hmm. but after the heating becomes viscous. could be more or less viscous. And I work in the product controlling the viscosity, for example, on 170 degrees to avoid problems with the extruder, because I think the development I was made was too viscous. And I was just asking, do you have notion that that will be too viscous, or you could go upper?
So do you feed the material in liquid form into the extruder?
I have a raw material that will feed extruder.
But in powder form or in liquid form?
Pellet form.
In pellet form, then it shouldn't be an issue.
Yeah?
Yeah.
Okay.
I mean, if it's too viscous, the only limitation would be at some point the load on the motor. The load on the motor of the extruder.
But there are also solutions for rubber, for example. So if it's just a resin in your case, it shouldn't be a problem. Because also like you can control the viscosity either by the temperature, also via the shear, because it's like shear thinning. And then for like very demanding applications like rubber, for example, in this case we have like different power units. In this case, it shouldn't be a problem.
Okay. I was avoiding that it was too viscous and could give problems in the extruder.
Typically, it would adjust the feeding.
Okay. Thank you.
So it's again, we don't know the viscosity, we don't know is the material fully mixed. We see what comes out, but we essentially don't know if it mixed to the degree with the properties that we want. Did it react anywhere? The crystallization, and what is the final product quality? Now it works. So to summarize this all a little bit, the mixer we use at the very beginning. It answers questions such how does my formulation, how does my recipe, how does my dry blend react to heat, how does it react to shear. We can observe the torque and the torque, time, behavior, stability, and diffusion behavior of special PVC blends. But there are also other applications such as fibrillation tests with graphite and PTFE, heat stability tests of all different kinds of polymers where you want to see at which temperature does my material start to degrade. When we go to the single screw extruder, we mostly talk about shaping questions. How does my formulation, how stable is my formulation within a single screw extruder? How stable is my melt, and can I get the shape that I want with it? And what process parameters do I need to get to the final stage of my product? And when we talk about the twin screw extruders, it's a compounding question always. How does my material mix? How can I process it? How do I have to dose it? And what kind of screw configuration do I need to get to the final product that I want with these properties? Okay, now there's a question: what can we do apart from these simple output we get from our extruders? One way would be to sorry, it's a bit delayed. Yeah. If you're, for example, interested in the rheology, we do have special dies which can be attached in front of the extruder. There is the slot capillary die and the round capillary die, which are both able to measure the viscosity of the polymer or polymer blend that goes through. Okay. How does it work? Here, for example, is a slot capillary die, and there are 3 pressure transducers attached to the die. One is right here in front of the die, and 2 are right in the die. And these 2 pressure transducers are used to measure a drop in pressure when the polymer melt is pushed through the capillary. And based on the pressure loss, the geometry of the slot capillary, and the volume flux of the material, you can then calculate a viscosity value for one specific point. This comes into two geometries, a slot capillary die and a round capillary die. The round capillary die usually is able to cover higher shear rates, since it's a lot thinner, but has a drawback: you need more measurements in the end due to an additional correction, since you cannot measure, with our transducer, you cannot measure the pressure inside of the small round capillary. Okay, here just an example of an inline rheological measurement for PVC applications. This is what the slot capillary die looks like when it's opened up. You can see here is one hole where we can measure the temperature inside of the die, and there are two holes for the pressure transducers. There's a fixed distance. This one is one of the smaller slot capillary dies with a distance of 50 millimeters between measurements. It has a height of 2 millimeters and a width channel width of around 40 millimeters. So for PVC applications, for average rheological measurements, usually a single screw extruder is used. But for PVC, we often use the conical twin screw extruder, because in the conical, since PVC is a very shear sensitive material, it works a little bit better in the conical, and within the conical, we also have the option to measure a normalized pressure profile, which was developed in cooperation with a customer of us, which allows us to be a bit more independent from the screw speed in the viscosity measurements. So how does it look like? Here for this, we were comparing a recycled PVC with a virgin PVC material. And this is how a measurement could look like. And usually you do 3 measurements at 3 different screw speeds. And for this specific example, it was very obvious that, or it could be seen that for the recycled PVC, we had a much higher torque level in the end, which resulted in also a higher viscosity. Okay. The MetaBridge, our software for the our whole drive unit software and extruders. You cannot hear me behind? Oh, I'm sorry. So once you've got all of these measurements with the outputs together, it is possible to calculate viscosity value. And then the software automatically applies a Rabinowitz-Weissenberg correction to compensate for the shear thinning behavior of the polymer, and also for the since the flow within the slot capillary is not really a laminar flow, and you have a slower flux at the walls of the slot capillary die, the correction is applied. Yeah. Another effect you see, especially with PVC, is once you just change something within the process, it's very likely that the color will also change. If you're getting too hot, you're starting to burn your PVC material. If you do have some additives that also might have an effect on the optical properties of the ribbon. So these are, for example, samples which were extracted from a viscosity measurement. You get these small ribbon, and it was and you could see that the PVC samples which contained the recycled material had a lot of a darker color shade. Depending on your application, in the end, this could as well affect it quite. If it's visible anywhere, you don't want to have the decoloration, so it's not really not really suitable for demanding film applications. Okay, So I think this part I can skip it a little bit over because we've already seen the Raman application. It's also almost, yeah, it's similar slides. I can maybe tell a little bit more about the setup. Right here you see the 2036D twin screw extruder. We likely fetched here a master batch together with an LDPE sample to get these red strip. A ribbon die in front with the fiber probe at the top, two pressure transducers, one pressure transducer in front of the die, and the below is the drive unit, the Meter Station 4, which is also standing in the back of the room, which we will later introduce a little bit more in the practical sessions. Yes, and with the Raman, we are able to just get a real-time inline and in situ analysis of our molecular structure during the process to just better understand what happens inside of the extruder. And it's possible, of course, to put it into different positions along the barrel line. So I'm gonna skip along these slides. I've already seen all of these before. And then we quickly skip to the next possibility. With Raman, we can cover the changes in molecular structures. With the FQA, which is short for film quality analysis, we can cover any optical changes in our cast film applications. So this is especially important when you're looking for a very pristine, when you want to produce a very pristine film. You can observe the quality of the film continuously with a camera which is attached to a winding system for films. So what it can do, it detects different kinds of defects in your foil. The software usually differentiates between holes, black spots, and gels. So gels are usually, for example, molten particles, which are unmolten particles included into the film. It could be when there is locally a different molecular weight somewhere due to which can happen, especially during recycling, or if there are sort of cross-link particles, which during the processing of reactive materials. Yeah. If there are some spots where are degraded materials, they can appear as black spots or additives that are somehow not really molten inside of the foil. If you have any contaminations like dust, sand, abrasions from mechanical parts, you often see them also as black spots. And of course, holes will also be detected by the FQA. Yeah, and this whole film quality inspections will become quite important with the increased use of recycled plastics. We see this especially whenever we do PET films. It's quite hard, as soon as it contains any recycled content, to get a very good film quality without any inclusions. Okay, how is it set up? The Univax, our winding system. Here we have the die exit. The film then is wound on these roller blades, rollers. The rollers are temperature controlled by a chiller, and then it is led through the FQA with the camera on top and a light source at the bottom. And at the end, the film is wound up in a roll. So there is a video. I hope it works. Yeah. So we have a light source at the bottom, which shines through our foil, and as the different defects wander through the line scan of the camera, we can see it in the program. So the camera has a resolution. The scan width is around 10 centimeters, and it has along the line scan, it's roughly around 4,000 pixels. So we get a lateral resolution of around 21 micrometers. Any defect smaller, you wouldn't be able to see anyway with your eyes. So for these applications, this one is fine. So what the software does, it detects a scan of the whole line with on the whole spectrum of gray levels, goes from 0 to 225, and then based on the gray level of the, which is different from the baseline of your polymer, you can differentiate between different defects. So for example, very bright spots is simply spots where the lightning from below shines through, and they are characterized as holes. Very dark spots are considered as black spots within the material, because there is no lightning at these points, and everything in between is then classified as gels. And the software essentially calculates the defect area, any deviations from the baseline, and counts the pixels and applies a sphere within the area to give the defect a diameter. And if you do this in a continuous process, you get a distribution of different types of defects of different kinds of sizes, which gives you an indication about your film quality. Naturally, this this whole process depends on the settings you use. What kind of defects do you want to detect, and the focus of the camera. So this is how the result of a typically film quality analysis looks like. You get a histogram that lists all the defects classified in different sizes already. You get a timeline of all of the effects, and you could also see when you changed your process conditions in the extruder, it will also translate to the FQA results in case it has an effect on your final product when you change, for example, temperature or screw speed. And then you also have the separation in the different sorts of classes. Okay. Now, combining all of these together, the mixer, the extruder, and especially the process analytics enables you to have a more efficient process development and material development. So you can combine. So you usually combine the mixer, the extrusion, and the process analytics to. With all of these tools, you have a very powerful kit to get a very efficient material and process development. Once you have a really good understanding and knowledge about your whole formulation, you can then easily scale up this knowledge for a production type of extruder. Yeah. This is all from my side. A big thanks goes also to our Andre Kaiser, which is our product manager for all of our extrusion devices. He also put together the presentation, but wasn't able to be here today. So big thanks to him. And this I would end my presentation. And yeah, thank you for your attention.